Arun. He will present the processing of hyperspectral remote sensing data. Now, the Mr. Mr. Rejit will present his presentation.
Okay. Already copied. Sir, let me look it. Thank you, sir, for your nice words of introduction. Good morning to all. I welcome you to my presentation on processing of hyperspectral remote sensing data. So in the last 2-3 days, you have enough lectures on basics of remote sensing, then different types of remote sensing, drone remote sensing, and many platforms for processing the remote sensing data, like NV, ArcMap, drone to map, side scan. And as yesterday, we have introduced the R programming also for processing the hyperspectral data. And today, I'm using the NV software, an overview of different tools that are available in NV software for processing the hyperspectral data, remote sensing data. And for this presentation, I've taken the Hyperion data for my presentation. So a quick review of the okay. So a quick overview of the Hyperion data, you can see. It's launched by the satellite E01 by NASA on 21st November 2000. And it gives the sensor Hyperion, which delivers the hyperspectral data in the range of 400 to 2500 nanometer with a spatial resolution of 30 meter and spectral resolution of 10 nanometer. And the sensor is at an altitude of 705 kilometers. And the radiometric resolution comes around 16 bit. And the mission got deactivated on 2017, but still we can download the Hyperion data from the website USGS Earth Explorer. You have to simply create an account and you can log in into it and you can download the data. So the data products of Hyperion, there are two data products I wrote. Both are the level 1 radiometrically corrected data product of L1R, and another one is both geometrically and radiometrically corrected level 1 GS data. So the Hyperion data we can download in two data formats. One is HDF and another one is GeoTIFF. So both the data format we can open in NV and we can do the processing. So with this, I'm starting the NV software. So now I'm stopping my presentation, then I will open my software. Then we can work in the software. And I will show you how to open the Hyperion data in the NV software, the different. And also one more thing, you can see two different band combinations. The RGB band combinations you can see. And this one is true color and false color combination. And the corresponding wavelengths also I have written in the board. You can see the water body, the vegetation, and also the built-up land, the bare soil, everything can be clearly seen with a resolution of 30 meters. So now I will open my NV software. Okay. So we can download the data, radiometrically corrected data, and both radiometrically and geometrically corrected data. So I will open first the geometrically corrected data and will show you. So in this geometrically corrected data, they are provided TIFF format. Okay, so and also we can see a metadata file of MTL. You can see. Okay, so this is the metadata file. So NV provides a quick opening of all the GOT files by clicking this MTL file. So I'm opening. So since it is hyperspectral data, it will take time. So the remaining processes, I am not showing to process any data. I will show you how to open the data and how to assign the values to the parameters and all. So this is just for opening the data. I will show you. Yeah. This is the geometrically corrected and radiometrically corrected Hyperion type. Okay, it's audible. Audible. Okay. Hello. Okay, this is the data manager. I think many of you have known the ArcMap software. So this here, you can see the layer manager, similar to the table of contents, the data manager, similar to the data catalog in ArcMap. How many of you have worked in NV software? Okay. Then how many of you have worked in this Hyperion data? Okay, nobody's. Yes, ma'am is there. Okay, so this is the toolbox where you can search the tools. So on the NV Analytics class taken by Sujay sir, he showed how to open the data, how to link the two display, then okay, how to open the data, the NV header file, how to link the two display. All these sections are taken by Sujay sir, so I'm not taking. So this is okay. In Hyperion data, there is some pre-processing techniques are there for Hyperion data. So first one is the removing of some bad bands. Bad bands are nothing, the bands that does not contain any information. So we have 242 bands are there for Hyperion data. So out of 242 bands, only 198 bands are non-zero bands. Other bands are zero. So apart from non-zero bands, there are some water absorption bands that will not taken for any analysis. Then some bands that comes between VNIR and SVIR overlapping regions, some bands are there. That bands also we will remove. So finally, out of 242 bands, we will take only 158 bands for the processing. So this is the first step that we will do. This is called spectral subsetting that I will show you. The next one is there are some sensor inherent noises are there. So you can see the continuous abnormal pixels. Sometimes the pixel value from the neighboring pixels, the pixel values will be very high. Sometimes it will be very low. So like that, these are all sensor inherent noises, which will reflect in the image like this noisy pixel. So we have to remove this strips, which is called along track destripping. So usually the along track destripping we will do with the help of some IDL, like Hyperion tools.sav is an IDL that we can download from the website and we can do the along track destripping. So the first one is Batman removal that I will show you. So for this purpose, I'm opening the radiometrically corrected HDF data format file. So it will ask for which sensor, E01 sensor, and this is HDF4 format. This is not geometrically corrected. Previously, I opened the geometrically corrected file. That's why you can see it comes in that way. So it's a simple vertical stripe. With radiometric correction, we have to do geometric correction. So here we can go for spectral subsetting for removing the bad bands. So in spectral subsetting, okay, I will show in the software itself. There is one tool. You can search the tool here. Resize data. So here the resize data tool, what it help this is, it will help us to resize the data spectrally and spatially. Okay. If you want to remove any bands from the data set, we can use this tool for removing that bands. And also we can do a spatial subsetting also with the help of a shapefile. Because for all the study area, we have shapefiles. So we can import the shapefiles to this tool. With the help of shapefile, we can do. We can draw a region of interest. And by using that region of interest, we can do spatial subsetting. Or we have the map coordinates, the latitude, longitude, the corner, latitude, longitudes. If we have, we can assign that corner, latitude, longitude values. We can do. By using an external raster data, we can import and we can do spatial subsetting. So here, I'm selecting this file. This is spatial subsetting. So by using map means by using a raster data, then vector file, ROI, EVF, we can import. Okay, we can import an array, and by using that array, we can clip. Simply equals to the clip function in Arcman. So now I'm not doing that part. Spectral subset. Okay, see 198 bands. So remain only 198 bands are non-zero bands. So NV will help. It will remove all the zero bands and will take only the 198 bands. So out of this 198 bands, again we can reduce the bands and make it into 158. So only 158 we will take for the final processing. So here we can see from the first 7 bands are zero bands. Then by pressing the control button, we can remove the bands like this. So we can see the number of bands is reducing 191 like that. By clicking OK, it will go. Then this OK, it will remove all those bands. So here you can see only 191 bands are taken out of 242. But I'm not running this because it will take a lot of time. It's a hyperspectral data. So like this, we can spectral subset. Okay, then comes the atmospheric correction. So we know that there is a component of atmosphere between the target and the sensor. So the reflected energy or the radiant energy that passing through this atmosphere, they will get some effects called atmospheric effects that will be clearly reflected in the output image. So while in hyperspectral data, especially satellite remote sensing, we have to do some atmospheric correction. So there are many techniques for atmospheric correction, like empirical ones are there, and also atmospheric correction techniques are like ATCORE, ATRAM, FLASH. So now I'm presenting the FLASH atmospheric correction. So I will open the software. Then I will show you. I'm removing this band. File, open. Okay. So this is a small subset of the region. To their extent. Okay. Then you can start with the flash. Flash atmospheric correction. Okay, so I'll tell you. Here we have to give input radiance image. So we download the radiometrically corrected image, no problem. But there are some conditions for this input image. The first condition is the input radiance image should be in the BAL or BIP raster data formats. I think you all know what is BAL, BIP, BASQ. Everybody knows this primary binary data formats of raster, BAL, BIP, and BASQ. For example, BAL, band interleaved by line, where So these are binary data storage for raster data. The first line of the first band, then the first line of the second band. Like that, it will be stored in BAL. So here, the input radiance image should be in BAL or BIP format. The second thing is, in the metadata, it should contain full wavelength at half maximum values. For all the bands, there will be full wavelength at half maximum. I will show you. See, the full wavelength at half maximum, these values are made. The second thing is the unit of the radiance. Anybody knows what is the unit of radiance? Microwatts per centimeter square, nanometer, steradian. So this is the unit of radiance. So for the flash atmospheric correction, we should provide the radiance image with the unit of microwatts per centimeter square, nanometer, steradian. We can check what's the unit of the radiance. Here I will show you. Okay, actually the unit should come here. This radiance gains. Okay, anyway, but the Hyperion data, the units are not in this format. It is, we need microwatts per centimeter square, nanometer, steradian. But in Hyperion data, the radiance is in the unit of watts per meter square, micrometer, steradian. So we have to multiply, we have to use a scale factor for converting these radius values. So usually from the literature says it should be 10. So we have to apply a scale factor of 10 for converting the radiance file. So full wavelength half maxima, then the radiance values, then should be in the radiometrically calibrated with the BAL or BIP format. So if it is not in the BAL or BIP format, there is one tool I will show you to convert interval. By using this tool, you can convert to BAL or BIP. Okay. Before running the flash atmospheric correction, you can use this tool for converting your raster file to BIP or BAL. So again, okay, that's about the input radiance image. Then the output reflectance files, we have to assign the name of the output reflectance files is directly a root name. So the scene sender location, the sensor type, flight date, flight time, all this information are available in the metadata file. Okay, when you download the data, you get a metadata file, a HDF file. You can open in WordPad, or in the software itself, there's a tool for view attributes. You can use that tool for view the attributes, metadata attributes, where you can see the flight date, flight time, sensor type, hyperspectral, Hyper. And also the scene sender location will come automatically. Let's input this image. Okay, use a single scale factor. I'm using 10. Okay. See, the long values automatically comes. Here you have to assign Hyperion, then flight date, sensor altitude 705 kilometers. I showed the first slide. For the specifications of Hyperion data, there you can see the sensor altitude. The ground elevation. So for this scene, this study area, you have to take the elevation, ground elevation. Then pixel size, it will be 30. Okay. Then flight date and flight time, you can get it from the metadata. Then comes to atmospheric model. So atmospheric model, by using this table, you can select the atmospheric model for your study area. If your study area in India, it usually comes in the latitude, longitude. You can see this latitudes. It will be throughout the year, it will be tropical only. So if in any other area, by using this chart, you can select the atmospheric model. The software, you can see different types of atmospheric model. So from this, you can select based by using that table. Then water retrieval, the water content of the pixel. So here we are using the water absorption regions. One another important thing is, in order to carry out this water retrieval, this band should be there in the imagery. So that's very important. So usually we will go for 1135 water absorption region for retrieving the water content of the pixel. Then the aerosol retrieval. Aerosol retrieval, you can see rural, maritime, urban, and troposphere. Depends upon your study area, whether it comes in a rural area, maritime, near to beach, near to coastal region, urban region, tropospheric. And also here also, you can go for aerosol retrieval, like water retrieval, aerosol retrieval, by taking the initial visibility. For clear visibility, we always give 40. If it contains haze content, a little bit haze content, it will be between 20 to 30. We'll give 20 to 30 kilometers of visibility. Dense haze is there, it will be less than 10. So based on our study area, we can assign this value source. Then spectral polishing is similar to spectral smoothing. For that, we have to give a smoothing window size, where I have assigned 9 bands. Then recalibration. Already the data is calibrated, but in Flash, we can again go for recalibration. Then advanced hyperspectral settings, where we can assign the channels. So always go for automatic selection to automatically select the channels from the input data. So these are the basic things that we have to give for Flash. So with this input parameters, we can run the Flash to any radiometrically corrected data. And I will show you the see, this is the before atmospheric correction. This is the spectra for vegetation. And after atmospheric correction, you can see the value ranges from 0 to 1. So usually after atmospheric correction, you can check that with the help of one.
Your phone. आपके पास फोन है ना अपना?
हाँ. So this is the reflected corrected data file after Flash atmospheric correction. So you can check by using statistics, compute statistics, just to confirm whether it is reflected calibration is done and the values are between 0 and 1. See the values. So by this, after doing the reflectance calibration, you have to check. Okay, it will help you whether it is converted. The reflectance values are converted. Okay, then. Okay, building the spectral library. Actually, day before yesterday, the Purushottam sir told how to collect the spectral signatures with the help of spectroradiometer. So here I will show you how to generate spectral library with the help of the ASCII text files. So ASCII text files are the output from spectroradiometer. By using that, how we can generate the spectral library. So here, I'm not running in the software, I will show you. So this is the spectral library builder tool that is available. So in that, we can import the data in ASCII format. And you can give the almost, usually the wavelength region comes in the first. The first column is the wavelength. And we have to assign the wavelength units nanometer. And any scale factor, if you want to apply, you can give a scale factor. Then the number of items, yeah, Yeah, finally, we can save it in spectral library file. I'm not running in the software, I'm just showing. You can get the spectral library builder tool in the spectral library builder. So you can use this too. Okay. So from the spectral radiometer, after doing all the pre-processing, you will get the ASCII format. So you can import that file to this spectral library builder, and finally you can get a. Okay. So this is the final output. So next comes to. Okay. Apart from spectral radiometer, we can develop a spectral library by collecting the spectral signatures from the imagery itself. That I will show you. Okay. So before starting, I will convert to FCC. So for FCC, we have to assign 803 for red, then 650 for green, then 548. Got it. So our aim is to generate a spectral library from the imagery itself. So this is the spectral library. Okay. So this is for the water body. Just press the shift button and click wherever you want. I collected for vegetation, I collected for water body, then for soil. So like that. So here you can collect the spectral signatures from the imagery. Then you can export into spectral library. And you can use this spectral library for doing classification or spectral matching with other data also, no problem. So this is one method. The second one is by using region of interest. So here I just click one pixel. For example, vegetation, I just click one pixel. So instead of that, this is the region of interest tool. So here, can draw a polygon, the water body, and collect the pixels. See, and here, this you can save as in XML format. Okay, usually we will save the region of interest, the ROI collected in XML format. Water body, ROI. Okay. So this is the region of interest. So see, by clicking that ROI, you can go to statistics, where you'll get the entire, all the pixels, the minimum, the standard deviation, mean. So we can go for the mean. Then you can export this as a spectral library. So here you will get the mean of all the pixels of the water body pixels, and you can save it as a spectral library. And you can use this for the further process. So three ways: from the spectral radiometer, from the imagery, and in the imagery itself using ROI, as well as from the single click. So this is one. From the using the ROI tool.
Can you show spectra and also appearance spectra, how they are different? saw and when you want to
So for that, so for the spectroradiometer, we have a vegetation. I will. Ah. Ah.
on the same floor.
Okay. Actually, I have to build from the ASCII file. Okay. This is the. Oh, okay. I have. So this is from the spectroradiometer.
Over there.
Ah. I have the spectral library file. We'll open that one. Load it, So the red one from the spectroradiometer and the pink one from the image. Okay, just comparing the two spectra. The red one from the spectroradiometer and the pink one I collected from the image. Okay. Now, extract. Okay, spatial subsetting. Already we have discussed. Okay, then the image classification.
So there is a spectral plot of the leaf taken in the ground. Which is taken something around 705. See the pattern in the sense. Here it is pure spectral relating to that. That is the pattern is set. You see a lot of wrong not that smooth. And that this is plotted on another there it is. What is that 10 nanometers? So that's the reason why it is so wrong. But the pattern set. The typical what are those bands or those
Yes, little bit shift is.
maybe the correction is not proper, but always you can see the middle range. The both pillars band. The band you can see there's a big so this is how the comparison you can see. So whatever modeling you do, for example, like distribution, application, the prediction model makes in between you can see that they are joined the straight line because they are not available. As I said, there are water bands. So only may not get a good model of the lab conditions, which will go down because of that. You have 2,151 variables when you do the spectrometer. Here you have only 158 that you may nanometer, and there are a lot of noises. One has to understand when you go from the lab conditions to the field conditions, there are many observations. Example. That's the reason why I said give a comparative evaluation. Same also for the soil you can look at.
One more thing at this point. We can do spectral matching techniques are there in NV software. So it helps us to match the two spectra. So before doing spectral matching techniques, we should do spectral resampling. As Sar told, one has a spectral resolution of 10 nanometer, another one have 1 nanometer. So usually at this point, we'll spectrally resample one with respect to the another. So in NV, you can get the spectral resampling tool. It's available. Spectral resampling. By using this tool, you can make both the spectra having the same spectral resolution. Okay. After doing the spectral resampling, there is another tool called spectral analyst. Okay, spectral analyst. So here what it does is, in spectral analyst, there are 3 algorithms I like: spectral angle mapper, binary encoding, and spectral feature fitting. So in these 3 algorithms, you can use for measuring the matching between the 2 spectra. So whenever you want to do a spectral matching process, you have to first of all, you should have 2 spectra. Okay, one should be a reference spectra and one should be from the image. Then you should do spectral resampling. After doing spectral resampling, you have to run spectral analysis. Okay, here 2 algorithms: SFF, spectral feature fitting, spectral angle mapper, and binary encode. So it will give a measure between 0 to 1. Okay, so 1 means best fitting. 0 means it's not that much fitting is not. Okay, so that 2 more tools. Then, okay, image classification. So image classification, yesterday and day before yesterday, many lectures were there on theory. So I'm not going into theory. Different types of image classification techniques: supervised, unsupervised, semi-supervised. So below you can see 3 output. This is the input data. Okay, you can see this is the input data. So this I did isodata clustering, simply unsupervised classification without providing any spectra. Okay, so this is the output. So next comes is SVM, support vector machine, where I use training sites. Okay, we can provide training sites. I didn't provide any spectra. I just provide the locations for the wherever the vegetation is there. I create an ROI, water body ROI, then soil ROI. I save it as an ROI file. Then I give that as the training site for SVM classification. Third, you can see SAM classification, where I give NMS spectra. So I already show how to generate a spectral library. So that spectral library we can give for SAM classification. And you can see the results, the 3 cases where you can clearly see the water body, vegetation, and so every time after doing a classification, the most important one is the classification accuracy. So NV there also it will help to measure the accuracy, like confusion metrics. Confusion metrics using ground truth imagery or ground truth ROI. So if you have ROI, ground truth ROI, so usually yesterday ma'am told this training site, whenever we do classification or regression, 70% will keep for classification and remain 30% for classification accuracy. So here, if we have the training sites, out of that training sites, 70% of pixels for water body, 70% for built up or the vegetation, we will use for generating a classified image by using any algorithm. Then the 30% remaining you can use here for checking the accuracy. So it will give you some measures like kappa coefficient, producer accuracy, then user accuracy, the total accuracy, total percentage of accuracy. So for example, if it has more than 70% accuracy is good. So based on your literature, based on the type of classification that you did, you can search the literature to get the accuracy assessment values. So this is all about the classification. So I'm not running any classification tool right now. So you can see the classification. Yes, sir. You can see the classification tools are there. Yes, sir. One more thing. Okay. Then I will. Okay. The last one. So I think the day before yesterday, while taking that NV analytics, somebody asked about the possibility of mixed pixels. And the speaker says that in drone, we are dealing with 3 centimeter pixels. So there will not be any mixing of features. But here it is 30 meter. So within 30 meter, more than one feature may come. So there will be a mixing of spectral signatures. So the problem is extraction of pure spectra will be the problem. So here you can see that I simply create an ROI, collect the signatures of water body, then vegetation, like that we can do. But we can make it sure that a pure spectra of water body or pure spectra of vegetation. So there are some techniques for generating the n-member spectra. N-member spectra means pure spectra corresponding to a single feature. So this is an advanced hyperspectral analysis workflow that you can see. These tools are available in the NV. Starting from the after reflectance file, we'll go do MNF transformation. So yesterday, madam told dimensionality reduction, okay, by using feature selection, feature extraction techniques. Yesterday, madam had taken. So there are some dimensionality reduction techniques are there, like MNF transformation, PCA transformation. So what it does is it will reduce the bands. So here we have 158 bands. So if you could able to, and all the 158 bands are not informative. The information content is very less in few bands. So we can remove those bands. So they will run MNF transformation. So like that, we will reduce the number of bands. Then we will generate the PPI pixel purity index. We will generate the pure pixels. From the MNF transformed data, we will extract the pure pixels with the help of pixel purity index. Then comes ND visualizer. After extracting pure pixels, we have to group it. We have to cluster. We have to make clusters of pure pixels based on their unique spectral characteristics. That we did in ND visualizer. After that, after making clusters of pure spectra, we will assign to a particular class. For example, one cluster of spectral signature we will assign to vegetation, one to water body. That is done with the help of spectral analysis. Okay. One more thing. And finally, classification. The same process, but here we will do some MNF transformation, PPI index, ND visualize spectral analysis. So you can see this is the MNF transformation. So this is the input data. So you can see after 158 bands are there. So you will get 158 MNF bands. So you can see the first MNF band, and this is the last MNF band. So you can see the information content. It's very less. So we can remove those bands. So usually after MNF transformation, we will take the first 8 or 9 based on the information content. Then we will do the pixel purity index, where you will get a PPI image. You can see bright pixels in the PPI image. So bright pixels corresponds to the spectrally pure pixels. So we will take only those pixels for the further process. This is the second step. And this is ND visualizer. So in n-dimensional space, we will plot all the pixels. And we can see that those pixels having the unique spectral characters get clustered. Okay. And we will make into groups. And after this process, what we'll do with the help of spectral matching techniques, if we have a reference spectra, of vegetation or water body, we will take the mean of this pure pixels and we will match with the reference spectra and we will assign that particular class. For example, class 1 vegetation, class 2 water body. And finally, any classification. Here I use spectral angle mapper classification. Any classification you can apply. Thank you, sir. Time is over. Thank you, sir.
I thank Dr. Rajesh for excellent presentation and informative session. Thank you so much.
Thanks.
We would like to felicitate with the token of love.
Thank you.
Now I invite Mr. Sunny Arya for next presentation. He will talk on processing of fluorescence imaging. He is a PhD scholar and processing. I request Sunny Arya to.
अभी नहीं आया
So good morning to all of you, and I would like to welcome you all to my presentation on chlorophyll fluorescence. So first of all, we will try to understand what is this fluorescence phenomena. So we know that atoms are made up of protons, neutrons, and electrons. So when we have electrons, these electrons are arranged in orbitals and like K, L, M, N. And when these electrons are arranged in orbitals, they do transition. So these transitions are caused due to absorption. So whenever light is absorbed by an electron, the energy is used for transition from lower ground state to an excited state. So this transition is the basis of fluorescence signal emission. So first of all, what is fluorescence? It is emission of light usually at lower wavelength than what is absorbed. And this phenomena of emission is called fluorescence. So it is very different from reflection. Now, the time delay in the absorption and emission of the signal is very much less, that is 10 to the power minus 8 seconds, and the energy of emission is slightly lower than what is being absorbed. This is why this is due to vibrational relaxation. So how this phenomena, this is a very chemical phenomena, so how this occurs in plants. So when we see the plants, when we see the plant biochemistry, then we see that we have pigments and chlorophyll pigments. And these pigments are present in the photosystems, in the electron transport chain, in the membrane, thylakoid membrane of the plants. So photosynthesis is the most important chemical reaction. And there are two types of reaction which are occurring in photosynthesis. It is light reaction and dark reaction. So light dependent reaction are occurring in PS2 with P680 as the reaction center. So in this reaction center is the cause of fluorescence signal generation. So PS2 is the major signal producer of the fluorescence. So mainly there are two types of fluorescence occurring in plants, that is sun-induced fluorescence and dark adapted fluorescence. Sun-induced fluorescence occurs in the light when light is present, and dark adapted fluorescence occurs when the plant are first adapted to dark and then it is exposed to light suddenly, that is light flash. So sun-induced fluorescence will be discussed by some other scientists. So I will rather focus on dark adapted chlorophyll fluorescence. So in dark adapted chlorophyll fluorescence, the phenomena which is being exploited for capturing data is Koski effect. We have to understand now what is Koski effect. In Koski effect, what happens? The first plants are dark adapted for 15 minutes. Dark adaptation means plants are kept for 15 minutes in the dark. And as you have visited Nanaji Deshmukh Plant Phenomics Center, so you might have seen the fluorescence sensor there. The same data is being utilized here. The dark chamber, you have seen the dark panel. So behind that 15 minutes, plants are being waited in complete dark. And after dark adaptation of this 15 minutes, it is exposed to a flash of light. So as the light is flashed, there is emission of signal in the far red region of the spectrum, which is being captured by the fluorescence sensor. So first of all, actinic light is provided, so minimum fluorescence is captured. Slowly, a saturating pulse is given, and due to this pulse, a maximum fluorescence signal is observed. So multiple images are taken in 20 millisecond interval, and through this multiple image, we can get the minimum fluorescence and what is the maximum fluorescence. So after using this, we can quantify the variable fluorescence. What is variable fluorescence? That is Fm minus F0. So this ultimately corresponds to the electron transport chain maximum quantum efficiency of photosystem 2. So it is an indicator of how efficient the photosystems are. What is the maximum efficiency of photosynthesis of the light reaction in the PS2? So it is a proxy measurement, direct measurement. Now you have already visited the Nanaji Deshmukh Plant Phenomics Center. There you have seen the fluorescence sensor. The first plants are being dark adapted, and we get the minimum fluorescence. After that, the flash of light is given. We get the maximum fluorescence through a series of images, and we get the ratio, the index ratio, that is FB by FM, as the ratio for maximum quantum yield. Now I did my PhD experiment in this and analyzed the FB by FM as well as projected area in the image. So we have seen that this is a nitrogen stress experiment. So these are on this side there is stress tolerant cluster groups, and on this side that wheat plants. On that side the signal is from susceptible wheat plants. So in the stress tolerant wheat plants, what we can see that in FB by FM, the control and treatment both are very close to each other, as well as in FB by FM as well as in area. So as we go to the stress susceptible wheat genotypes, wheat recombinant inbreed lines, that is wheat genotypes, then we can see that there is large gap between the treatment and the control. So both FB by FM, that is photosystem efficiency, is decreasing, and the area is decreasing. The fluorescence, variable fluorescence is decreasing as well as area. This is caused due to nitrogen stress. The nitrogen stress causes this less efficiency of the photosystem 2, and this less efficiency of the photosystem 2 is being captured in the FB by FM signal which we got from the images. So again, this is the pair plot. We can see that the tolerant genotypes are darker, and it has higher FB by FM, which we got from the fluorescence image, and as well as area is higher. So now the fluorescence image which we got from the stress tolerant and stress susceptible genotypes. The first we will take a look at stress susceptible genotypes. In this, the FB by FM is less as well as area is less. And in stress tolerant genotypes, what we can see that in both in control as well as in a stressed condition, the area is being maintained throughout the life cycle of the plant, as well as we have high FB by FM signal in stress as well. So we can see that through fluorescence sensor, we can differentiate between stress tolerant genotypes and stress susceptible genotypes. Also, we can use machine learning approaches for yield modeling. So I did yield modeling, and we got a good correlation as well as low RMSE and MAE values for support vector regression in stress condition. So we can say that fluorescence sensor can capture stress conditions, abiotic stress phenomena very well. With that, I would like to wrap up my presentation. Thank you. And so in the part of the image processing pipeline, the main thing which is being used during image processing is the open source software, which is Python. So in that, what we did, we selected we calculated the mean of all the images. There are multiple images which is being captured throughout the time. So we calculated the mean of the images, and the maximum image, the mean corresponding to the maximum fluorescence image is being taken, and the mean corresponding to minimum fluorescence image is being taken. After that, both images selected, and FB by FM ratio is being calculated. So open source software Python is being used for this image. Yeah. So the libraries which are being used is NumPy. These kind of libraries are being used, as well as OpenCV. So you can do using Python. Python, you can do image processing very well using the power of NumPy. Okay, thank you. I guess there are no questions, so thank you.
Thank you, Sunny, for giving a brief introduction about the fluorescence imaging, how it is useful for the stress characterization. You can explore yourself how this fluorescence imaging is used for the early detection of stress, because fluorescence is considered as an indicator of early detection, even though the symptoms is not appearing on the leaf. So for that purpose also, that fluorescence imaging can be used, and accordingly management can be done in the crop. So at this juncture, I would like to thank Sunny and facilitate with the program.
Thank you, sir.
He is ready. So now break for tea. Then next speaker, whether first field visit will be there, or that depending upon the speaker is available.
So good morning. We had sessions till now on multispectral, thermal, RGB, and hyperspectral again from Monday to Tuesday. So we are almost towards the end phase of the program. So we thought of we should take up something on the LiDAR remote sensing. What is LiDAR and how LiDAR can be used on the airborne platform like UAVs, and what are the information can be retrieved. Much detailed discussions on the LiDAR and fusion with the hyperspectral for accurate retrieval of the information and thermojacking. LiDAR is one of the important input that will be discussed again on Monday and Tuesday when we do pre-processing of airborne hyperspectral data. So today we'll be talking on the LiDAR UAV remote sensing. So we have with us Mr. Rahul Jain. He's a very good friend of mine. Very recently we met, but time is not a factor to be so close and getting the frequency match, and that's what happened with us. So, and we understand his the capacity and his experience, expertise over the years, what he was doing with respect to LiDAR and also many other UAV data acquisitions. He has have a very vast experience with respect to data acquisition, processing, and also different applications. So I thought this is an opportunity to invite him to share his experience, how UAV LiDAR is useful for agriculture. So with this background, Mr. Rahul, this is a World Bank funded program, as I informed over email. And we have many young researchers, students who have joined with us. In addition to students, we have many young scientists, assistant, associate professors. They have joined from many parts of the country, online and also offline. So I hope this short exposure on the LiDAR remote sensing will be very useful to them, and they will build up some of those programs, research in future. So thank you very much for accepting the invitation and coming over here. And hope this interaction will be very useful.
I hope so.
Thank you.
Thank you. Good morning. Thank you very much for inviting me, Dr. Sahu. And it was a wonderful introduction you gave me and about your conference. And I wish all the best for your this session. My name is Rahul Jain, and I'm the co-founder and managing director for Matrix Geo. Matrix Geo is a company which has been working in the field of remote sensing and LiDAR for almost 15 years. So as far as the today topic is concerned, we are going to learn a little bit about the LiDAR systems and how it works. What are the implications which can be, pertaining to forestry as well as the agriculture, and what are the different parts into that. Beside this, we also work into remote sensing technologies like satellite image processing and of different type of satellites, mainly the RGBI, red, green, blue, and infrared, as well as we also work in hyperspectral and multispectral domain as well. Okay, so let me start with this. So this is all about us, that what we are. We are a company of experts of LiDAR and photogrammetry. Plus, we also work in geology a little bit. And we are a company, basically a geospatial, we called ourselves as geospatial consultants. Why? Because we also help in engineering projects too, like the bridge projects, railway projects, or any type of road projects, kind of dam projects, irrigation projects. In these type of projects, we help the engineers in designing and providing them the survey data. So this is the areas where we can actually help in different type of domains like land management, network analysis, incidence mapping, corridor selections, and spread diffusions, topographic analysis, demographical analysis. So these are some of the areas where we can actually help you in different domains. So these are our technology work portfolios. We work in a digital photometric services, whereas we work in aerial photography. The aerial photography can be done by several means, like the actual manned aircrafts, as well as the helicopters, and nowadays it is drones. And then we have to, once you take the photographs, then you have to process it with different parameters. So the first process is called as digital aerial triangulation. So this is one of the things which we do. And then you have to do the 3D vector mapping, which is basically a digitization of the map, but it is specifically into a 3D workstation that is called stereo mapping workstation. So in that we have to do the stereo mapping. And then once you have the stereo mapping, then you can generate different type of digital terrain models. In another terminology, it is also called as digital elevation models. Okay, and then when you have the digital elevation model and the aerial photographs, so when you club up both together, that becomes the orthophotos. The orthophoto is a real photograph, which is distortion-free image. So we also work in the digital orthophotography. And then there are several products out of it, that different type of thematic mappings are there, like mine mapping, irrigation mappings, different type of mappings are there. So we do that things as well. So there is another thing is coming up in the market, and it is very, very happening at this time, that is called digital twin models. This is also called digital 3D models. So there are several cities or several places are there where you can make the digital twin model. It is basically a 3D model, which has been derived by utilizing the different photographs and the LiDAR data set, which makes you a different, photorealistic models are there, but they are not the plant models. They are the 3D reality models. Okay, so in GIS and remote sensing services, we work in the utility, automatic mapping and facility mapping as well. And then topographic mapping is one of our key part. Then we have different type of data captures and other things. These are something which we are doing. And in LiDAR, when we come to the LiDAR, everybody knows about the LiDAR, I hope so. LiDAR is a light detection and ranging. It is a sensor which you can see right here in my hand. This is a Velodyne LiDAR sensor, which is having near about 6 lakhs point per second capacity to capture. Okay, so LiDAR is some device, whereas you send a light rays, and when it comes back to the sensor once again, it calculates the distance. When it calculates the distance, it can generate the point. So those points are called point clouds later on, and it gives you the information. If it is connected to GPS as well, you can see a small device here. So when you see the GPS is having a coordinate of X, Y, and Z. And there is also another instrument is called IMU. We will talk about that later when we go to the main slides. So that particular instrument is called complete LiDAR system. So in this LiDAR system, it can be utilized for the power lines, piping, oil and gas, forestry, mining, as well as in highways and roads, railways, telecom, coastal management. And right now, we are also using in forestry as well as in agriculture. So in data processing, we have several types of data sets in LiDAR, starting from different density, starting from 2 or 3 point per meter square to it can go up to 200 point plus the density. That means 200 point per meter square density of the point cloud when we take up the data from the LiDAR data sensor. And that can be used for different purposes. Like if you have a smaller density, then it can be utilized for forestry as well as for the agriculture. But when you come to a monument or a structure or the plant, then you need a high density point clouds. So in that case, that the point density will go to 500 to 200. Okay, and then we have the different type of engineering services which we talked about is the pipe design, roadway design, highway design, railway, all these things are there with us. So these are our core competencies areas where we are working at this moment. Like topography, as we already discussed, land use and land cover mapping, educational facility planning and state level, health facility planning at a state level, watershed planning and privatizations, cut field analysis, corridor mapping, watershed mapping and wetland mapping, forest mapping. So these are some of the things which we are talking about, and these are the areas of working. Landslide zone is one of the core area where we are working right now. So this is something we are talking about at this moment is the airborne lidar sensor, but we'll talk about the different other sensors and the other related services related to lidar. So what is lidar technology and its basics? So lidar actually stands for light detection and ranging. The ranging is of the reflecting object based on the time difference between emission and reflection. That means the scenario is something when the light goes on a distance on a path, and when it object to something and then it reflects back. It calculates the distance, and on the basis of distance, it calculates its XYZ position. That is what is called it generating the point cloud with XYZ object. And it can be work in day and night, because it doesn't require only the day visions. So it can actually work in night as well. And this particular information is this particular type of system is called active photogrammetry. It is a part of photogrammetry remote sensing, but it is called as active photogrammetry because it gives you the direct results. Whereas in passive photogrammetry, which is the normal RGB photogrammetry, where you have to take the photograph and then you have to process it to get the results. So it gives you the direct result. That is why it is called active photogrammetry. So this is a little history of LiDAR, where the first optical sensors were developed in 1960, and the first airborne LiDAR ranging tried out in 1960. First, in late 1980, the use of GPS made accurate range measurements from airborne. It is basically in the University of Stuttgart, Germany. And then beginning in the profilers are there. The meaning of profilers is there is a kind of different type of LiDAR system which are rotating. There are 2 or 3 different type of LiDAR system. One is the static LiDAR, where you have the single beam lasers, and then you have the rotating LiDARs. This is basically a profiler. There are several LiDAR sensors are there which are rotating in the 360-degree directions. There are some profilers like they go in this kind of directions. So these particular things are called profilers. Okay, so profilers have been introduced in 90s, and the airborne LiDAR scanners actually introduced in 1990. Then we start utilizing it, and then after they coupled with GPS and IMU. The meaning of GPS and IMU is, if you could just see here, this particular machine, this LiDAR scanner is right here, but there is a red machine in the background. It consists of 2 special instruments. One is called GPS and another is called INS. GPS, everybody knows, I believe, the global positioning system or differential global positioning system. Or I would rather say it is a GNSS system, that is Global Navigation Satellite System. Okay, so the another aspect, the abbreviations I talked about is INS, Inertial Navigation System. The meaning of these 2 are different. One gives you XYZ positional accuracy or positions. The another one is giving you the gyroscopic rotations. That means rotational angles. For solving any kind of information or any type of point information, you would require to solve the Helmert equation. The meaning of Helmert equation is you have to solve basically 7 parameters. When you solve x, y, z and roll pitch O or omega phi kappa, which is the rotational angles, then you solve the Helmert equation, the scale will automatically come. Okay, and you get the position of that particular point. So we'll move a little forward to this. This is all about this system is. So now we understood that laser ranging can give you a precise location of a certain points by utilizing the distance measurement tools. And it depends upon satellite positioning. It also depends upon the inertial measurement units. So you can see here in this picture, we are showcasing the GPS positioning X, Y, Z, and then the tilt angles, different type of rotation angles of the aircraft or the IMU. So if your aircraft is moving in any direction, it is heading is there. Okay, and then you have different type of rotations. So this particular location, this particular movement, which is having along the nose and tail, this is called generally pitch. Okay, or omega, sorry, phi. Okay, and then you have this kind of along the wings. This particular movement is called roll, as well as in another language it is called omega. Then you have the another directions, which is basically along the axis. So if it goes like this, okay, this is generally called as kappa, or this can be roll pitch yaw. Yaw and kappa is same. Okay, so this is called, these type of 3 direction rotation angles are there, and GPS, you know that X, Y, Z is there. So when they club together, they solve the Helmert equation, and this is also called as orientation. Once you have the orientation, then you have everything sorted. And lidar scanner is right there in the under the aircraft. Okay, so this is connected to this particular machine, these particular 2 instruments. Whatever the scans we are taking, those scans are connected to GPS plus IMU and gives you the perfect and accurate XYZ positioning. So this is a kind of a system which generally we put it in the high-end aircrafts. This has a capacity of more than 12 lakhs points per second, and this can go up to the altitude of 3,000 meters. It has a ranging capacity of 3,000 meters. So here you can see is, so GPS will be differently corrected. Differentially corrected means you have to have a base on the ground, and that has to be connected to the rover, because that particular instrument, the GPS, is there on the aircraft. So that has to be connected at the same time when your base is running in the ground. I hope that you people are well aware of differential GPS. It is a kind of a science where you have a base and rover. Base has to give you the coordinates, the coordinate which is known, and then those coordinate has to be transmitted to the rover at every time whenever it is running. Both the system has to run in the same time frame, so that the base will always give the correction to the rover. Rover is nothing but it is connected to the lidar sensor in the aircraft. Okay, so that rover is having GPS coordinate differentially corrected by the base on the ground. I hope you understand that particular thing. That is the reason why it has been called as differentially corrected. And then then only it can give you the centimeter level of accuracy, because you have to have coordinate which is connected to some base or some known coordinates. Otherwise, it gives you the coordinates in S-bars. The meaning of S-bars is satellite-based augmented system. So whatever the GPS coordinate you are getting on the basis of 5 or 6 satellites, you'll get it, but they are not corrected to any of your known coordinates until you provide the base to that. And the inertial measurement system, which you can see here, roll, which I was showing you, that another way is roll, pitch, and yaw. And then we talk about the little bit about the wavelengths or the lidar ranging. So there are two different type of lidar systems available in the market. One is called bathymetric lidar, and another is called normal lidar, normal infrared laser lights lidar. So if you are working with the 1064 and above nanometer wavelengths, so in that case, it is above the surface. But if you are going beyond to that, that means near about 500 to 600, the blue-green lasers are there that can, go underneath the water as well. Generally, the lidar system available in India is above the ground only. Okay. So characteristics of the lidar is generally right now the lidar system is available where you can get the accuracy from 3 centimeter to 15 centimeter depending upon its quality, make, and its height. And the height means the distance from where you are taking the ranging the parameters. It depends upon its range. There are systems available from 50-meter range to going above 5,000-meter range, but the quality and the costing are severely different. Like you can see this particular lidar sensor is here. It's about 5 to 5.5 lakh rupees, but the range is about 100 meter only. It's not more than that. The result, which I will show you a little just after this, then you will be able to see that how much area and how the lidar sensor actually works, what type of lines are there, how much points it can calculate, everything. So it should be capable of collecting millions of points per second or per hour. So like I said that this can take near about 6 lakhs points per second. That means it can take millions of points in an hour. So that should be the capacity of this type of system so that it can take several number of point clouds. And it can also, produce the different type of densities, starting from smaller density to the bigger density, like per meter square. Density of the point cloud means the point per meter square is the density of lidar point clouds. Okay. And when you have lots and lots of point cloud, you can create a intensity image, because when you have lots of points, you can actually create the image. But that image is not going to give you the RGB picture, but it gives you a kind of an intensity image type of picture. So what lidar is? Lidar is a active sensing system, which we talked already about. कैमरा ऑन है, बंद करना. Okay. Sorry for the interruption. What we were talking about is active sensing system, which we already talked about, that lidar is an active remote sensing technology, photometric technology. It works on the principle of reflecting the waves, light waves, and then it comes light sources. And then ranging of reflecting the object based on the time difference, which we already talked about. I think we talked about all these things. So what LiDAR is not, where it cannot work, and what the meaning of it. Target must be visible within the selected EM spectrum. That means if you are working with 1064 nanometer ray, that and you are targeting an area which is hardcore black, a coal type of black, it will not work out in that area. Number one. Secondly, if you are putting anywhere which is non-reflecting, like a mirror is there, it will not work. Third, if it is like water kind of thing, it will not work. It will not reflect you back. So those are the areas it will not work. But if you're working with a right wavelength, that means if you're working somewhere around 500, 550, that means it can actually penetrate the water and it can go beyond to that. So it depends upon your electromagnetic spectrum. Okay. So it will not work in rain or fog. Yes, it can work, but the rain and fog is something which is having kind of moisture, and rain is also having some moisture. So when it goes to the object, the rays goes to the object, it will not reflect back, it will divert somewhere most of the time because of the prismatic effects. So once this effect will be there, it would not be giving you the right results. So that's why the system is working, but it is not giving you the right result because of some different effects. That is the reason why it is not advisable to utilize the LiDAR system during these kind of issues. And when you have lots of clouds, if you are using below the clouds, you have the same effects. You might face some moisture inside the sensor as well. If you get this moisture inside the sensor, the rays will not go beyond to that. Okay. Now, not able to penetrate the trees. Yes, it can penetrate the openings. There is a myth that LiDAR can actually penetrate the vegetation. It is a big myth. However, this is not possible at all. The LiDAR is nothing but a sensor which can give the light source. If light can penetrate underneath the trees, that means you can actually see, and your LiDAR sensor can actually see beyond to your trees. However, the best thing is the LiDAR sensor comes with the multiple returns. You understand? There are multiple returns kind of thing. That means they try once, they try twice, they try thrice, and there are several different type of LiDAR system which can go to up to 7 returns. So at a single instance, they can go for several returns. So when you have multiple returns, that there is a possibility when your system is moving and you have a multiple returns, there is a possibility that you can go underneath the trees because you are seeing the same ground from different perspectives. Okay, so we'll talk about this thing as well. So you can see there is a small thing here. The LiDAR instrument consists of the system controller and transmitter and receiver. We have a receiver with this drone as well, whereas you have the receiver, and when the aircraft moves with the line of sight, scanning is generally done. You can see this, just see this. I'm just going back again. So one, this is the nadir position, this is the backward position, nadir position, and then forward position. Can you see this? So this is the way that it actually moves on across the track and light across the track. And then here you can see is point spacing is repeating frequency is there, pulse repeating frequency is there. You can see here there's a ranging, there's a scanning mirror is there. Then you have a different scales, like if you are flying at a height of 100 meters, that how much points you require. There's a capacity of every system that you need to give the system to a time that if you're flying with this system at a speed of 100 kilometers per hour, it will give you less point cloud. But if you fly the system with maybe 30 linear kilometer per hour, the point cloud will be higher because it works on a principle of point per second. So if you want a denser point on a certain area, you have to fly or you have to go a little less speed to have more point clouds. If you want more point clouds, less point clouds, but you want the same accuracy, still we would suggest you to go with a lesser speed. The designed speed for these kinds of system is generally 30 kilometers per hour to maximum 60 kilometers per hour. That depends again upon the sensor to sensor. Okay, so the flying height is the important aspect which you need to work upon while you are using any type of LiDAR sensors. You need to figure out that the sensor has been designed for how much ranging. There are sensors from starting from 50, 100, 150, 200, and then it again from 200 it directly goes to 1000, from 1000 to 1500, and then 1500 to straight away it goes to 3000 to 500,000 meters. But those sensors are extremely costly. They may be more than 12 crores. Like this sensor, it's in lakhs, but that goes to in crores. And they have a different IMU systems as well. So the flying height, speed is important part, and the scan angle. The meaning of scan angle is if you are putting the sensor in this fashion, so it is taking the rotation and data set beneath this and above this. But if I'll put the sensor like this is the angle. It is covering the whole area. Okay, and you need to mount a sensor in such a direction that the area which you wanted to actually scan should be covered. Okay, so there are three different type of LiDAR scanners are also there. One is airborne. Secondly is terrestrial laser scanners, which are generally utilized for bridge inspections or bridge scanning or monument scanning like that. And fourth is generally called as mobile laser scanners. So what is the meaning of mobile scanner? The same type of scanner can be put on the car and can scan in one go. It works on a car or railway tracks. Okay. Now there are another thing is this. You can see that how do you wanted to have the footprints. There are several type of LiDAR scanning is there. Like in this, there is a circle is going on like this. Okay, so when it goes in a circular mode, this is one of the pattern. It can go into zigzag mode. This is another pattern. It can go in profiling mode like this. As a parallel line. So this is the third pattern. So there are 2, 3, or 4 different type of patterns whereas it actually scans. Get it? So it depends upon your speed and the type of sensors or type of system you are using. So this is basically having a circular cycle. It goes like this. So generally it is having a irregular pattern because they wanted to give you a better point clouds. So here you can see that it can emits more than 1 lakh pulses per second. This is the minimum scenario, but there are different systems. Like our system is having near about 6 lakhs pulses per second. Okay, and light travels depends. These are some things are written that time is equal to 2 R by C. So here is the R is something ranging and divided by 2. So that depends that how it travels with the time and calculates the point cloud. So this is something which changes in every time scenario. Depends upon your sensors. So type of sensors we are talking about is, as we talked about, there are 3 different type of sensors. So we'll just try to understand. So airborne sensors are there, topographical lidars and bathymetric lidar, and then terrestrial is mobile and static lidars. So of course, it can be airborne sensors are generally on the fixed wing or helicopters. Infrared sensors are there, which we already talked about those things, that what lidar is and how it actually works. We also worked on bathymetric lidar, that how the bathymetric lidar is working. There is the only difference is that works on a less than 500 meter, 500 nanometers. Terrestrial lidars are the system which collects a very high dense point clouds, and it, because they are static in nature, you are putting it somewhere here and they are collecting the information again and again. So they gives you a point density of more than 200 points per meter, or sometimes they give you in thousands as well. Generally utilized for rail surveys, bridge surveys, chimney surveys, monuments, building structures. So they are generally utilized for reverse engineering purposes or the inspection purposes. Sorry. So mobile lidar is something which also have one more specific thing. Along with the camera, along with the lidar sensor, we also put the 3D camera as well, so that it can create the point clouds along with the textures with the help of camera RGB picture. So camera RGB picture and IMU will give you the perfect orientation. Lidar is already there. So when you combine all 3 together, that gives you the actual point cloud in RGB format. So that is the only different systems, but this can be also applied to any of airborne system as well, because you can also put a camera on board as well. Topographic lidar is the same, which we talked about it. It can be utilized for forestry, hydrology, geomorphological planning, urban planning, ecological planning, coastal engineering. How it can be utilized to coastal engineering? So you know that there are several countries which are sinking at this moment in the world. So lidar is a device where you can actually utilize the real application of it. How? You can scan the whole coastal line every 6 months or every year and make a difference. So you would be able to understand that how much it is, eroding, or somewhere it is getting distorted. So in those particular areas, you can make the break walls, as well as you can make some kind of arrangement so that that particular area will be, safeguard. So those things can be handled with the help of this kind of technologies. UK is utilizing that. UK Environmental Agency is utilizing it for last almost 10 years, the same technology. Static lidar. So what do you mean by static lidar? So you might have understood that static lidar or the terrestrial lidar is more or less same, but there is a system like this particular is a profiler lidar. It has something which is rotating inside, whereas static lidar is something like a camera where you have a sensor looking forward only in the one direction, but still it gives you several number of point clouds. It goes like 45-degree angles. Okay, it's a bird eye view kind of scenario. Okay, so in that is it's a very new kind of technology which DJI has also introduced. You might have heard about the IVA lidar system, which is a basic small laser sensor. L1 is the prototype they have developed, which gives you several number of point clouds, near about 3 lakhs point per second. So that is the capacity of that particular system with multiple returns of, I think it is 3 returns per second. So those are the parameters of that particular lidar system. We talked about the bathymetric lidar as well. So this is the picture which is showcasing you that how the mobile lidar system actually works. And the example of mobile lidar system, as well as the on the right side, you can see it is a Leica 360. It is basically a terrestrial lidar system, which is having a range of near about 600 meters. And this is bathymetric lidar output. This is hydrographic or bathymetric lidar is same. So you can see that it can actually see the underneath of water, and how it will basically work is double wavelength is there, blue and green and NIR. And blue means less than 500 nanometer, and when it goes, then it can penetrate the water up to 50 to 60 meter, depending upon its water turbidity. And actually it can scan the underwater and can give you the underwater digital terrain model. So this is the beauty of this particular hydrographic lidar or bathymetric lidar. There are some space-borne lidar systems is also upcoming, that is generally called SAR, synthetic aperture radar. So they are kind of a lidar system as well, but it's a very early stage to say about those things. Now we can talk about a little bit upon the lidar post processing. That once we have the lidar system, then we have to know that from where its positioning is coming up, whether it is being connected to base or not, as we talk about, and what is the speed of that, what is the IMU, quality of IMU is there. There are several types of IMUs are available. All of are having, I'm pretty sure that everybody is having the smartphones right now. Every smartphone is having IMU, because whenever you rotate that, it can calculate the roll, pitch and yaw. But the quality of that particular system is very cheap. Hardly $1 or $2 chip is there. That's called MEM-based IMU. Okay, so a very small chip is there, wherever we have a very small type of tiny nano tool is there, which goes here and there and calculates the roll, pitch, yaw. Whereas this is MEM based, whereas we have the another one that is called optical gyroscopic based IMUs. The costing starts from 3 to 4 crore rupees for that. So those are the systems which generally utilize in the high-end ALMS, airborne lidar mapping solutions. Okay. And then ranging. So there are the 4 parameters you should know to complete the first phase of the LiDAR system. The first thing is positioning XYZ, which is speed, IMU, or I would say INS, and then the range. How much range is there in a particular system? And the angle. Angle is where you are mounting the system, what you actually wanted to measure. Then we can derive to the position of X, Y, and Z finally. So this is the key. This particular image is the whole key of the LiDAR system. So in the post-processing, what exactly you are looking at? Can anybody tell me that what exactly you people are looking at from the LiDAR data? You people are looking at only X, Y, Z positioning or the point, which may be n numbers, but you want a precise X, Y, Z. Am I right? And that depends upon the previous picture. So there are 4 important factors. One is your differential GPS. Second is your speed. Third is your INS. Fourth is your ranging capacity, and then where you are mounting in. Mounting is of course in your hand, wherever you want it to base. But there are 4 important parameters into this. Okay. So once you have all these, then you need to calculate it with the, you need to georeference it with the base. Once you georeference it with base, then you have the locations of the lasers in 3-dimensional parameters. And then you can easily calculate your everything, and it actually gives you everything automatically. Post-processing means you just need to calculate with your base, nothing else. And then you need to provide different type of coordinate system to that. You can of course provide WGS84, or you wanted to calculate it in another UTM coordinate system. You can also do that. There are possibilities like that. And you can of course generate intensity image. You can utilize along with your orthophotos. That is also possible. So everything is possible into that. I will just showcasing you that what kind of data sets is there. You generally have mass points. You can see the power lines, poles, tree canopies, grounds, all these type of things will come. And here it is that how we are showcasing that the different type of multiple returns can help you out in this. Once you have a LiDAR system, then pulse we go and then go back to the sensor. As soon as the system moves a little bit, then you have the another pulse, it goes and it will give you the different angle. Once it gives you the different angle, it can penetrate, it may penetrate the different canopy. So it actually hits the ground this way, the first return and intermediate return, last return. And you can see here, I'm giving a live example of this particular area. The first return will giving you this much of point clouds. The second one is giving you more point cloud. Can you see this? This point cloud is there, and this is the current situation. This is the actual situation. This is the first level of return, whereas you can see there are less number of points in this particular area where the vegetation is there. And in the second return, then you have more point clouds. And in the third return, there is again some more points are there. In fourth return, there are some more points are there, but they are already been, filtered. So this is the way that you can develop, and with the help of lot of number of point clouds, you can create this kind of intensity image. So now we can talk about the accuracies. Accuracy is basically which is required by the client, or the maximum capacity of a system. The system generally starts from 2 to 3 centimeter, and there are several different type of errors are aligned to that, which is GPS errors, and then IMU errors. The IMU errors is generally in the degrees that how it can create the problems and create the problems in the actual positional accuracies. Okay, so mostly currently the systems available in the market is can give you 2 to 5 centimeter of accuracy. There is a possibility like that. So generally the point cloud data in this format are there: XYZ intensity 0 to 255. That means it is a color coding number, intensity for the intensity, and returns. How much returns are there? Whether it is from the first return, second return, third return, as per the ASPRS standards. Okay, so direction of the scan, and then edge of the flight lines. So this whole scenario, one scan is called the one scan, just like your image. When you take a picture, it's something like that only. Okay, and it also gives you the time of the GPS. GPS times are generally there in the UTM formats, universal time format, UT time. Okay, ASPRS standards are these. You can see this. There are certain classification code which are standardized, whereas it has been written that different type of classes are there. Never classified, created, or never classified. When you take the LiDAR, it comes in only and only in 0 class. When you classify it automatically, then it goes into different classes like this. You can of course make your own classes. It is a kind of a layering system. This is a point cloud which I'm showing you, and then you can generate the digital surface models, digital surface model and the orthophoto, and then you can generate the contours, you can generate the hill shades, you can of course filter the point cloud and can figure out whether this is a forestry area or this is the kind of area where you have heavy vegetation or low vegetation, silos, built up areas, each and everything. In fact, you can also calculate the wires. Here are some applications of this. So mapping of corridors like road, railways, tracks, pipeline, waterways, landscapes. These are something which you can calculate or make the topographical maps of it. Mapping of electrical transmission lines. It is one of the most important area where the LiDAR application is quietly utilized across the world, because there is a major issue is when you have power lines, there are trees nearby, so they infringe with the power lines, and the fire probability will be there, so they need to cut down those trees every year. For that, they need to do this kind of survey, which is going for the infringement study. Digital surface and digital terrain model preparation for different type of irrigation schemes, drainage pattern analysis, any type of site suitability analysis, tunneling, each and everything. This is one of the biggest role player right now. Okay, so of course there are so many things are there which I think I can give you this presentation later on, but slow. It is also utilized in avalanches studies, glaciology, oceanology, everything. In oceanology, of course, we use the different type of sensor, which is bathymetric LiDAR, but in glaciology, we use this kind of sensors. Okay. Measurements of wetlands, watershed areas. In forestry, we can calculate horticulture, we can utilize this for the tree height, crown diameters, tree densities, biomass estimations, determination of the forest borders. So these are the areas where maybe you are interested in. And you can generate the true ortho images. What is the meaning of true ortho is? True orthos are generally been created by utilizing the digital surface models. Surface model is something when you have the height of certain objects. Okay, when you have a object height, then you can create the digital true orthophotos. Here you can see a little bit that the LiDAR can actually give you this kind of catenaries, wires, roof, different type of trees, and it can also give you any structures cross sections. So these are some of the areas which are very, very good to understand by utilizing the LiDAR. And now we are talking a little bit about the railway systems, where you can see that this is a cross section. Here, this is the area where we are talking about a sleeper. The sleeper is here. You can see that this particular area as a sleeper, and these are the rails, rail tops. So this whole geometry can give you a better picture, and it is very, very good to understand the track geometry. And if you wanted to make another line right here, you can create the complete digital elevation model and create the another line. It is very, very useful for the making the new alignments, okay, and understanding the track geometry. And then it can be utilized for different type of road planning and development. You can see that here it is road reconstruction and development, and it is a tunnel area, and there we have lots of point clouds which is showcasing that particular roadways. And this is for the pipeline surveys. In the urban planning, smart cities, map building footprints, identifying building height, determining the line of sight. You know that the line of sight is one of the major problematic area for all the airports in India or across the world. So generally what happens is when you have an airport, it has a vicinity that you cannot actually make big height buildings. So line of sight for the funnel range of the aircraft has to be clear. For that particular study, the LiDAR is generally utilized. When you have a LiDAR, you can easily calculate the nearby heights in 1 or 2 go. That's it. And you can calculate the line of sight very easily. So smart cities, yes, it can be utilized because you have to do the different planning, and you have to have the digital terrain model and the virtual earth kind of scenario, or the digital twin model, wherever you need to make the another area of interest or develop area of interest, that can be possible utilizing this. So in the hydrological modeling, there are several point of applications like monitoring dams, reservoirs, risk analysis, stream channel determination, identification of watersheds, okay, for floodplains determinations, modeling of directional flow of water, where the water is actually moving on. Everybody have seen the disaster which has happened in Kedarnath. So if we had the study of that particular area, wherever we had the water flow or drainage flow accumulation as well as its routing, so that was never ever had happened at that time. Now this particular thing has been done. That means the drainage pattern analysis has been done. Geology is something, the understanding the geomorphology and figuring out the different type of landslide and potential landslide areas. This can be easily figured out with the high density point clouds. And it is very, very useful, the mine mapping. You can see that you can make different type of digital elevation models of the mines and create the mine mapping. And you can also do the kind of volumetric calculations when you have a wonderful, digital terrain model. So here in the forestry and wildlife, what you can do is you can figure out the different type of tree species identification, vegetation characterization, tree height measurements, timber volume calculation. That means actually you can calculate the girth of the tree. So you can figure out the timber volume calculation, identifying the terrain under canopies. This is the best thing about the LiDAR, that it can actually look inside the trees. So you can calculate the terrain underneath the trees as well. So urban forestry analysis is another thing, is determining carbon sequestration, biomass calculation, habitat assessment, and understanding the connectivity issues. Connectivity issues here, meaning is if you have a jungle inside, forest is there, but you are not able to understand which route is connecting to which route. So there is a possibility that you can figure out the route which is impacting the forest as less as can be possible. So there is a possibility to figure out the shortest path as well as less impact in the wildlife. So understanding the characteristic of the LiDAR data here is, it is a full waveform LiDAR, is giving you this way around. That the meaning here is, it is not clear, but the same thing which I was talking about is wavelength is returning 3 or 4 times. So once you have the different type of returns, then it goes underneath. First return, second return will give you different characteristics and give you different results. So this is all about this particular figure here. Okay, it's in detail right now. So you can see that the scanning of LiDAR is, now we can talk about the swath of LiDAR. So meaning of swath is, if your profiler is somewhere around 100 meters, so how much area it can cover, the swath? Generally, it is 1.5 times to your height. So if it is 100 meters, that means it will cover 150 meter swath. So that is the general idea of understanding how much swath it can cover. Okay. Sometimes it is 2 times as well, but in the 2 times, maybe it covers, but right on the edges areas are not good enough to calculate the right heights. In the disaster management, it can be utilized because it is a faster and active technique. It gives you the result immediately. So in that case, wildlife, fire assessment, risk analysis, improving application for oblique imageries. That means if you have the oblique data set, you can figure out that how much data is actually there and how far it is there. Okay, so it can be utilized for, understanding the, sometimes, I don't know if I should say this, but let me just tell you, but there is a possibility to do the surveillance on the borders by utilizing this. Okay, there's a possibility. Okay, improving applications of the oblique imagery. This is the application of that particular thing. A smoke and chemical plump analysis, slope analysis for the fire modeling. If there is a slope and you are going with the fire assessment of that particular area, you can do it. Coastal management, we already talked about, but just give you a little brief. The dune monitoring, coastal undulation, land substances, slope stability issues. There are several areas where you have the slope issues, and beachfront management is also possible by utilizing this. Tsunami and hurricane undulation mapping. That is also possible utilizing the LiDAR or photometric techniques. Nearshore bathymetric and beneath mapping is possible by utilizing the bathymetric LiDAR system as well as with the normal LiDAR system. When you club both together, you will be able to understand that up to where this is risk-free zone, and tsunami or hurricane when possible, that how much area it can actually, under the pursuit of risk. So that can be calculated by utilizing this. when you have the data sets of that particular area. This is a little that intensity you can calculate and time. When the coastal tide will hit to the shore, that how much time you have, that is the intensity which you can calculate with utilizing this. Application in agriculture to identify which area their field to apply the costly fertilizer to achieve the higher crop yield. LiDAR can create a topographical map. Of course, yes, the topographical map can be easily created with the slopes and sun angles to the farmlands. Another application of LiDAR is beyond crop health and terrain mapping in orchards and vineyards. Sensor detects foliage growth to determine its pruning or other maintenance needs to take place, detect variation in fruit production, or perform automatic tree counts. So the meaning here is you can calculate when you have the data set with you, you can calculate the height easily. That means you can see the growth of trees or growth of your crop. You can figure out the acreage. Okay. You can also figure out if somewhere there is a problem in crop. You can also figure out with the RGB eye sensor as well as with the LiDAR sensor. You can also perform that. If you have a tree area, then you can also calculate the tree counts easily with the help of this LiDAR data. So this is the application where we are showing you that how it is going. High, medium, and low yield areas. I'll just go a little faster. So these are some of the projects which we have done earlier. This is the experience what we have. That's it. Thank you. And right now I would like to showcase you the live demonstration of LiDAR. So this is the machine you can see here. Can you see? Everybody can see the screen. So right now the sensor is in my hand. So I'm just moving it here and there. So you can see this particular area. And if I'm moving it, then it is showing something on the screen right now. So this is the LiDAR sensor, which you can see it is having 16 channels. So you can see 16 different lines are there. So when you put it on the system like this, if I'll just put like this, and it is calculating like this. Everything is going like this. Now it is showing the whole area. So as and when you required, you can mount it in your direction of area, but you have to calculate it, and then it gives you the live feeding of LiDAR data set on your desktop or in your machineries, and you can calculate it later on. And this gives you the precise calculation up to 3 to 5 centimeters. Okay, if you have now any question, that I would be delighted to answer any of that. Thank you very much. Is it over? No, it's okay. I'm done. Okay, no, I have one more thing. Screen share is going on. Screen share. Okay, so I just forgot to share one more thing with you guys. So here is a live data sets from one of the area in India. So you can see some data set right here. This is a trajectory where we had actually flown in this area. these are the two trajectories where we've flown, and these are this particular area. As you can see here, there are a lot of trees. Can you see the tree here? These are two different scans of the same area. And we have calculated the digital elevation model utilizing the same LiDAR system. And when we crop the trees here, then what would be the result of the bare earth model? So this is the bare earth model here. You can see we have removed all the trees here. So you can see that this particular area is clear, and you have number of points. And you can calculate the contour lines from this easily. There's a latency here, but it will come. You can see the red lines are actually the contours. You can also measure the cross sections. You can see that the cross section is also here. So you can measure anything, L section, cross section, any type of contours, geomorphology of that particular area. There is a possibility for doing all these things, all that kind of analysis by utilizing the LiDAR system. So I gave you an example of this. So if you have any questions, then I would be able to answer you. Thank you.
This is DTM or DSM?
This is digital terrain model.
And earlier yours went with trees.
This is your digital surface model along with the trees. So when you cut off the trees and everything, then it becomes digital terrain model, as simple as that. Yes, please.
So how deep does this penetrate inside the water?
Currently, the systems which are available is it can not go beyond 70 meters. This is the current situation.
So that is where the blue light stops.
Yes. Forest species mapping is something which we are covering two different type of sensor. One is the LiDAR sensor along with the RGB sensor as well. RGB eye sensor rather. So those sensors will give you the type of signatures or the patterns of that particular species, that what type of species it could be on the basis of height, color, and its patterns that it is showing you. So on the basis of RGB majorly. Resolution can be 3 centimeter to 10 centimeter, depending upon your height of those particular trees or those particular areas. Sometimes you are flying in valley areas, and in valley areas you cannot follow the terrain most of the time. So you have to fly on a certain height. Sometimes it is more than 1,000 meters. We have seen, we were flying in some area in Jammu, which is near to Kishtwar, Kishtwar is one of the typical area in that particular region, whereas the distance is more than 1,800 meters. So we were flying somewhere around, our AGL was hardly 200 meters. That AGL means average ground level height. was hardly 200 meters, but when it goes to the valley, the height deviation is more than 2000 meters. So the resolution at that time would be going more than 20 centimeters. So in that particular time, there are certain issues. So your camera has to be perfect. If you are flying in certain areas, you need to calculate it with the height to your performance ratio. For example, if you are flying with 24 megapixel camera with the 150 meter height, okay, so which has to be your AGL, average ground level has to be 200 meter, 150 meter. So you will get a resolution of near about 4 centimeter. Okay, so there are calculations by which you would be able to calculate the resolution easily. That generally called as GSD, ground sample distance. Yes, please. Yes. One is circular, another is zigzag, and third one is sinusoidal. This one is circular, yes. Pardon me? Yes, this one is circular. Yeah. I'll just showcase you one more time. Oops. My system has gone. Sorry.
What you are scanning from the surface of the.
Yes.
So, but it is scans 360
Yeah, it is scanning in 360-degree direction because this particular camera is moving in 360. But there are systems which are static in nature and it always see this way around. Right now, this particular system is there. You can see here. But what about this particular area? It is of no use. Okay, but system is capable of handling 360. Right now, whatever the data we will take, it is about 180 degree only. So because up to here, it gives you a swath, it gives you the swath up to there only. But it has a capacity to develop 360. And this system, this is the same LiDAR system which has been mounted on the Tesla cars. It is also utilizing for the autonomous cars and autonomous braking systems. It has also been utilizing in high degree auto collision systems in Indian Railways as well. Any other questions, sir? Thank you.
Suppose I would like to fly this in the high park.
Right now?
No, just I want to fly to get the vertical accuracy. What is the accuracy will give? Because most of the time
It can give you near about 5 centimeter of accuracy.
5 centimeter of accuracy.
Yes, or from your top points.
And you were saying something on the HCL. Suppose you are in a hilly terrain.
Yes.
If you try to fly with keeping a constant HCL, then you will get that should not be a resolution issue. There is no height variations because it follows the terrain.
When it follows the terrain, there is no problem. But generally in the high steep slopes, working with the drones, with the terrain following is very, very difficult because in those particular areas, generally what happens is you do not have the right digital elevation model even from the SRTM. So when you do not have the base data set with you, you would not be confident enough that you are flying with the hardly 100-meter altitude difference. It would be very difficult to ascertain in most of the areas. The height difference may give you setback that your drone may crash in those areas. However, as far as technology is concerned, it is quite possible.
No, like we have now Spain drones where we try to maintain 2 to 3 meter height always, irrespective of crop stand. Suppose crop stand is a chickpea, which is a this much height, whether crop stand is a maize, is a bigger height, then it maintains that distance. So for that purpose, there is a terrain follower sensor they have put, radar they have put, so that automatically it goes up, maintains that HCL.
I understood your point.
So you can put a sensor for that purpose to maintain that terrain, then you can go for it.
Yes, there is a possibility, like you are talking about a basic lidar sensor or the optical avoidance sensors or barometers, like those sensors are there, which you can put underneath this, and they make a distance of 4 meter to 5 meter distance. But sir, with the high-end lidar system, it is sometimes very difficult to ascertain the heights. When if you're working in BVLOS mode, it is absolutely not possible.
Actually, the challenge comes if at all you put that sensor, is the sufficient data points to see. Suppose you are flying through a hill
Hmm.
or in a forest, like you said.
Yeah.
In that case, it maintains the height because canopy height is there. But canopy height keep on changing because number of the tree species. There will be small height, there will be bigger height.
Yes. Yes. Yes.
Okay, you have a sapota, you have a mango,
Yes.
or you have a coconut. Altogether, that gets changed.
Correct.
One point. Second point is you have some gap areas. In between, you don't have anything.
Yes.
Then what will happen? The drone will go down because it's following the edge.
Correct.
It follows the sensor. There you don't have a manual because you are doing automatic mode. So it looks for the sensor HL height. So now it is over the mango. In between mango orchard, there are nothing. So the sensor looks down, it has to go down. Then it will be done. Because when it goes down, then it will hit to the tree or two. So that's what happens most of the time. That's why those kind of sensors are not allowed to do that kind of terrain analysis when you fly with this kind of sensor in the terrain where you don't, when it goes down, you don't come back, or if you get hit, then everything is gone. Maybe whatever money you have spent on that, I think it was something, including software and all those things, it would be around 40 lakhs, right?
The hardware, only the lidar sensor is there. It's about 1 CR.
No, I'm talking the low cost one.
The low cost one is this one, which is about 6 to 7 lakhs.
Yes, that's what I'm saying. That with the software, it was something around 30 to 40 lakhs.
Yeah.
So you see 100 lakhs sensor flying inside and something goes wrong. You will really get that.
Yes.
Anyway, it's very interesting. Thank you so much.
Thank you. Thank you very much, sir.
Mr. Rahul. So, on behalf of we would like to give a token of appreciation. Thank you. Thank you so much. Okay. Yes, see here. It's done. So, Saad, come back at 2 o'clock because we have online class that's going to come in University of Valencia, Spain. So, there will come to be careful. So, quickly, come back.
Hello, good afternoon, everybody. Can you hear me? This is Jochem speaking. So if anyone can confirm if you can hear me, then we can start.
Yes, yes.
Okay,
It's
thanks a lot.
perfect.
Okay, good. So good afternoon, everybody. Let me share my screen.
Is the name? Joe, just wait.
Okay, can you see my screen?
Yes.
Um,
We'll wait for 2 minutes.
so I'm ready to start.
Hello. Are you able to hear me?
Yes, yes, I hear you.
Yeah. Wait for 2 minutes.
Yes, please. Sure.
Joe, can you hear me?
Yes, yes, I hear you, but I don't hear anything.
Okay. What I was asking is, how are you? How is the weather there?
Everything is fine. With whom I'm talking now? So you will tell me when I should start?
I'll tell you just in a
Okay.
minute.
Okay, perfect.
Still, participants are over lunch break and they are yet to join.
Okay.
Some of them are already there.
Uh-huh.
We'll take 3 minutes to ask them to join.
Perfect.
So this class is up to 3:15, 3:30. Is it okay?
Yes, 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 absolutely. I'm around.
Yeah, yeah.
So there are people in the room and they can see the screen, right?
Yeah, yeah, perfectly.
Okay.
We can see your photograph also.
Okay, excellent.
Yeah,
And then
I
there are
wish
also
it could
people
have been here
online. Yes,
again.
yes, me. Me too.
So I don't want to make you wait. Let me start before Dr. Joachim starts. I want to take this opportunity to thank him very much to accept our invitations to give this wonderful talk on the fluorescence spectrometry and ready to transfer modeling of vegetation. So Dr. Joachim,
Berles received the Master of Science degree in Tropical Land Use and in Geoinformation Science, both in 2005, and the PhD in Remote Sensing in 2010 from Wageningen University, Netherlands. His dissertation focused on the spaceborne spectro-directional estimation of forest properties. Since 2010, he has been involved in preparatory activities of European Space Agency's Fluorescence Explorer mission, that is called FLEX mission. His research interest includes retrieval of vegetation properties using airborne and satellite data, canopy radiative transfer modeling, and emulation and hyperspectral data analysis. He is the founder of a software called ARTMO, which is very much popularly known worldwide, and we have been using very much for radiative transfer model retrieval, modeling for biophysical parameter retrieval. In 2017, he received a European Research Council starting grant to work on the development of vegetation products based on the synergy of FLEX and Sentinel-3 data. He's also the co-chair of Sensesco Coast Action, a European network that focuses on the optical synergies for spatio-temporal sensing of scalable ecophysical traits. He published over 120 peer-reviewed articles. Now in 2023, he just received European Research Council grant on the exploitation of upcoming FLEX data for continental to global vegetation productivity and stress estimations. I'm so happy to go through your short note about you. I'm very proud of you. And Dr. Job, so we have students here from the different part of the country, almost pulling them together, around 40, 45 students, and also some young researchers. They're around 20 to 25 who are very fresh scientists and assistant and associate professors in different institutes in India. And also we, as I mentioned you, we have many participants online. They are also have joined, and we are live streaming throughout. Anybody can join, even globally. So right now, I don't see how many other, the 80 participants are right now there, maybe because of the lunch break or whatever. So Dr. Joe, again, thank you so much. And I request you, please go ahead. Thank you.
Okay, thanks a lot, Dr. Rabi. Thanks for introducing me, and good afternoon, everybody here in Europe, Spain. It's still in the morning. It's 9:42. I hope you can hear me. Also, I hope you can understand me. I'm native Belgian and living now in Spain. So my English accent maybe is a little bit different as yours, but I would suggest if there are questions or if there's something you do not understand, please put it into the chat. And probably after the presentation, we can go through the questions and have a discussion if there's time for it. Let me quickly introduce myself. So I'm a PhD in remote sensing. And for the last 10 years, we focused on the retrieval of vegetation properties, especially from satellite data. And that will also be the talk for today. We will focus on both optical data from classical satellite missions, as well fluorescence data, which is a newer data source that will be recorded and retrieved from the European Space Mission FLEX. So with this, I will give you the title, Fluorescence Spectrometry and Radiative Transfer Modeling of Vegetation. I have two presentations prepared. One will be about this FLEX mission, and the other one will be about more on the methods of retrieval of vegetation properties. So well, welcome everybody, and let's start. And maybe first I will give you an overview of, let's see if, right, you see, okay, yes. So I give you an overview of the ESA's Earth observation fleet. And in fact, the ESA satellites, they are ordered according to three pillars. One is science, which are the fundamental missions for scientific applications, so for new science. The second pillar, these are the operational missions. These are the Copernicus missions. They are also managed by the European Commission. And then the third pillar of satellite missions are for meteorological applications, so weather forecasting. Our interest here above all are on the science missions, and I put it in the red box. There is this mission that we've been working on for the last 10 years, and it's called FLEX, Fluorescence Explorer. So with the science mission, what we mean is that these are rather smaller missions. They are not intended for operational use, but the data can be freely downloaded, but it's more for scientific applications and as a technology demonstrator with the hope that eventually the technology will become mature enough that it also will become an operational mission, perhaps eventually a Copernicus mission, like one of those sentinels. So the FLEX mission is rather small. The satellite also looks like a fridge. And we are really trying to push forward new science, especially on these fluorescence retrieval for better understanding of vegetation. And the FLEX mission also will orbit together with the Sentinel-3. Later talk more about it, but that's why I put also that Sentinel-3 in the red box. So these are the main missions of interest for us. FLEX will be launched by 2025. Sentinel-3 are already launched some years ago, the first one in 2015, and the second one was then in 2018, and now Sentinel-3C will be launched next coming years. So let's have a look to the Earth, our living planet, providing feed and food for our world population. This is the essential of our life. At the same time, of course, the Earth entered an era of anthropogenic changes with increasing temperatures. And this implies that our forests, especially our croplands, are subject to stress with consequences loss in productivity. Also, at the same time, our croplands are under increasing pressure to produce food and feed and to ensure our global food security. So this asks for timely monitoring strategies that enable early assessment of vegetation health, and so to keep track of our croplands, how they respond to changes, how our croplands are subject to stress, and how we can deal with it. Also, precise information of vegetation productivity is needed for understanding and tracking the dynamics of the terrestrial carbon balance over Europe and across the world. So this boils down to the question of how to quantify photosynthetic activity. And only by spatially inferring the photosynthesis dynamics, we can monitor more productivity, adaptation, and resilience of vegetation across the world. Now, when zooming out at the continental or global scale, vegetation tracking is achieved through satellites, Earth observation satellites. And for Europe, the European Copernicus fleet, that's in charge of it, mainly uses the Sentinels and especially Sentinel-3 for global monitoring. However, it's very important to realize that optical missions, they only record reflected radiation. So they can only know some information about the greenness of our vegetation, but that can then be derived to productivity. But with optical data, with reflectance data, we have no information of if the vegetation is currently under stress, because it can stay green, it can look good, but perhaps inside the plant is already under stress and therefore not optimally photosynthesizing, eventually leading to loss in productivity or even maybe in dying of the plant. So for this reason, there is also an alternative source of information, and which is information that comes from the plant itself, namely fluorescence. And this fluorescence is a signal that's coming directly from the photosynthetic machinery that is emitted by vegetation. And if we can track that, although it's a very small information, we have information of the actual status of our croplands. And that's the idea of the Earth Explorer FLEX mission, is to record and detect and interpret the fluorescence information, so coming from the plants itself. And with this way, we have a direct link to what the photosynthetic activity of the plant. FLEX is planned to be launched by 2025, and we are currently preparing the mission and also preparing the processing chains. So what is this fluorescence? Fluorescence is the glowing of plants when they are photosynthesizing. You cannot observe that by your naked eye, but in the lab with specific filters. And when plants are subject to strong light, and then afterwards you record it with a filter, you can see this glowing of these plants so that you are aware plants are photosynthesizing. So what's happening inside the plant? The largest amount of radiance that is absorbed by the leaves are used for photosynthesis. And also some parts are dissipated for heat. So some parts are transmitted or reflected. But a small part, an excess of light of the photosynthesis, is re-emitted as fluorescence. Basically, the fluorescence is part of the photosynthesis system, and it goes through a cascade of mechanisms of photochemistry, conversions of heats by means of electrons that are brought to an excited state within the plant, and then the energy is then released, and a small part of this released energy is emitted as fluorescence. This fluorescence is not just a single band signal, but it's a broadband signal with two peaks that are reflected by the photosystems called photosystem 2 and photosystem 1. Also at the same time, because of these heat mechanisms, these are the so-called xanthophyll cycle within the photosynthetic apparatus. These xanthophyll cycle also can be observed by optical sensors in very narrow band over a specific region, the so-called PRI, photochemical reaction or reflectance index region, within the 555 and 600 nanometer region. So there are two ways how to observe how well plants are photosynthesizing. On one hand, by means of recording fluorescence, and on the other hand, aiming to detect if the PRI region, if there are some changes, so we have some idea about what is called the non-photochemical quenching. That's the simple way, and that is well observed within the lab. But when moving outside to a field, it's somewhat more complicated because, of course, there's also reflectance and absorbance mechanisms taking place within the leaf, within the canopy, and eventually also throughout the atmosphere. So a proper understanding of all these mechanisms, so the radiative transfer of the leaf, canopy, and atmosphere scale are needed to understand what actually this recorded fluorescence, what it means, and how it can be related to photosynthesis. So let's have a closer look to photosynthesis, and I'm sure you already know of the basic principles. So when a leaf, a plant, a leaf, when it's photosynthesizing, it has water that is coming from the xylem of the plant. There is CO2, which is coming from the stomata. And of course, there's also energy coming from the sunlight. The photosynthesis is a highly regulated process that involves a cascade of electron transport to fuel carbon fixation, the carbon cycle. And fluorescence is emitted from the cores of the photosynthetic machinery, from photosystem 1 and photosystem 2. And basically, when light reaches the photosystems, most of it is used for photosynthesis, but a few parts of these electrons are being released, they jump out, and that's the fluorescent signal that we observe. Since there is a photosystem 2 and photosystem 1, there are two ways when fluorescence is being released, and that's why there's this two double peak into fluorescence for photosystem 2 first, and then at the lower energy, so at higher wavelengths, photosystem 1. Now let's have a closer look into how this mechanism works, and we see here an overview of starting with a tree. Water enters, CO2 enters, and when we come inside the leaf in the stoma, we see the chloroplasts, and inside the chloroplasts, there are the so-called thylakoids, where these photosystems are active and where they receive the light, do the chemical interactions, and release the fluorescence for photosystem 2 and photosystem 1. So that's one way how we can detect remotely, even from space, the fluorescence and thus the activation of photochemistry and the photosynthesizing. On the other hand, as a protective mechanism, when the plants receive too much light, which happens on the daily basis, so around noon, the second mechanism also starts to kick in, which is the so-called xanthophyll cycle, where the pigments, the pool of pigments these molecules, they start to change a little bit for protecting themselves. And in this way, they block the photosynthesis, and the energy by these changes is so transmitted as heat. And that is the so-called MPQ, non-photochemical quenching, the MPQ cycle. The MPQ, because of the pigments are changing with precise hyperspectral sensors, we can also observe these small changes. So we are aware that the plants are protecting themselves to an excess of light, and that MPQ is playing a role. So there are three mechanisms you need to remember. On one hand, the main mechanism is photochemistry. So light reactions driven by photosystem 2, photosystem 1 for the photosynthesis entering the Calvin cycle and eventually photosynthesizing and assimilating carbon into energy for the plant and new materials. Then a small part is being released as fluorescence, and it has these two peaks because of the role of photosystem 2 and photosystem 1. And then a remaining part that is released as heat by changing the pigment pool, which is called the MPQ cycle. These two of them we can observe. We can observe fluorescence with hyperspectral sensing. We can observe the MPQ with hyperspectral sensing. So having information of the two pathways of the energy gives us ways how to derive information whether the plant is actively photosynthesizing or not. So we have an idea of the health status of the plant. And also in this way, we can derive if the plant is under stress or if it's producing just fine. Now let's have a closer look in how does that work for these radiance fluxes, the energy fluxes. I like this figure a lot because it gives the general overview from the radiance point of view. And when we start with the left part of the figure, the black line, that is how the typical radiance is when it's at the atmosphere, so top of atmosphere radiance. The gray line, let me show with a pointer. Gray line is how radiance would be, so that's this line here, how radiance would be at the bottom of atmosphere, so when it's entering our planet. And from all that energy, the green part, and we see also the units, the green part, that is the part that plants and leaves absorb, right? So they absorb a small part of it, a fraction of it. Now, what happened inside the leaf are these photosystem reaction centers. Most of it goes to photosystem 2. Then the smaller part goes to photosystem 1. Photosystem 2 and 1, they release fluorescence, and these are these red lines that go underneath. So we see the profile of photosystem 2, photosystem 1. Part of this energy that is released, so these electrons that are released out of the plant, yes, they play again, they can be reabsorbed by the leaf. So there is this feedback mechanism that goes back into leaf absorbance, and eventually that will again take part into the photosynthesis of other leaves, no? Because of course the radiative transfer flows through the canopy, and all these leaves, they interact. And that's the fluorescence part. Part of the energy eventually is used for the in the Calvin cycle for photosynthesis and assimilation of new materials, so the gross primary production, and we can so calculate further towards net primary production. You see losses due to transpiration and so on. But what is of interest for us is from a radiative transfer point of view or a sensor point of view are these fluorescence signals. Fluorescence for photosystem 2, photosystem 1. Eventually, what is being emitted to space again, since there is this reabsorption, there's influence of satellite space, is just this very small fluorescence signal. We are talking on the orders of 2 watts, an order of 2 compared to the fluorescence as it's emitted from the leaf, which is on the order to 6 or 8. So it's a very small signal. You will never see that with your naked eyes. And even sensors, they need to be highly sensitive in order to track that small signal, taking into account there is the role also of the canopy structure, the atmosphere, and so on. So to track that part, and even when you have this part tracked, because of all these other mechanisms playing a role, it's still very hard to interpret that information directly to photosynthesis, since there's also this energy that is lost through MPQ. So also that kind of information needs to be known. Now let's have a see this kind of figure, but from another point of view, from the scaling point of view. And it's from the same paper. I like this figure a lot because it gives us an idea of how fluorescence is changing over the different scales that we are measuring. So starting from the chlorophyll molecule, this would be the complete fluorescence signal that is being released by the chlorophyll molecule within the photosystem. But then all these transfer and scattering mechanisms start to play a role within the thylakoids, the chloroplasts, the leaf, shoot, canopy, making that because of absorbance and reabsorbance, especially in the red part that is being absorbed again by other leaves, you can nicely see how the fluorescence signals changes over the different scales. And eventually, when we aim to observe that from space by satellite, where we can only observe for a few bands, we will see this very narrow signal, which has nothing to do anymore with the original signal, making it very complex on how to interpret this signal towards what was originally happening within the chlorophyll molecules. We can also see because of the all the other factors that play a role. So let's quickly go through it. So the thylakoids, they do this PC1, PC2 light reaction centers to capture the electrons. They also, part of the energy goes to alternative energy sinks. They are chloroplast movements and reabsorption taking place. Further at higher scale, stomatal mesophyll conductance, photorespiration, morphology of the pigments, reabsorption at the canopy scale. And that's what matters when we start observing from airborne or drones or space. There's the role of canopy structure. So again, reabsorption and scattering effects, canopy vertical heterogeneity, measurement geometry. And then at the ecosystem scale, we also have the role of atmospheric effects, functional diversity of vegetation, background effects. So you can realize that all these factors, they play a large role of how fluorescence is influenced over all these scales. And fluorescence is just one part of the story, as we said before, because of course, also part of the energy is converted as heat through the MPQ mechanisms. And I like a lot these figures where we can see how much of the energy is used for photosynthesis, which is the green part, MPQ, so the heat mechanism, and this would be for a cold spring day at 15th of April. And fluorescence is actually quite stable, and it's only a small part of the total energy that is being emitted, meaning that and this is the key message, that fluorescence alone is never enough to obtain understanding about the photosynthesis. Also information of the MPQ is required. And these mechanisms, they change over time. For instance, in the second figure here, in 17th of July, the fluorescence, well, it's more fluorescing because there's more energy, more sunlight over the plants, is larger, but still it doesn't vary that much. In fact, the photosynthesis and the MPQ are the more important driving mechanisms. So we need also to know about the MPQ mechanisms together with fluorescence in order to know how much of the energy is used for photosynthesis and how well the plant is producing new material. And eventually we can upscale to the global scale, because with our satellite sensors, we can measure these fluorescence already. Some satellites already do that job, but MPQ still remains a challenging aspect on how to quantify that from space. Okay, so let's move on to the next slide. And one moment, my computer is waiting. I hope you can still see the screen, because here at my place, it says the computer is not responding. And maybe it will help if I can switch off my camera, if that's okay for you.
Yeah, please.
Yes, because I think it's overloaded. And yeah, it says that my PowerPoint, I need to restart my PowerPoint. So I will try to do that quickly. I apologize. Maybe it will help now when having switched off the camera. One moment. PowerPoint tries to recover. Okay, now I will put it on again. Okay. Let me try now to share the screen again. Okay, and now you should see, I think it's this one. Do you see the screen again?
Yes.
Okay, okay, yes, so sorry for
Thank you.
the inconvenience. And where were we? Yes, we were here, right? Exactly, is that correct?
Yes.
Okay, yes, okay, so I apologize, and hopefully now there will be no more problems. So let's move on. And now let's have a look to, so the fluorescence, we have earlier seen the mechanisms. So let's see to the sensors. As this fluorescence, it can be measured in the lab, and it can be also measured outside in the field. Now, there's a very big difference between measuring fluorescence in the lab and in the field, because in the lab, that is much easier, as there we can make use of specific filters of the incoming light, so that it will only take the light where we can see the fluorescence. Meanwhile, outside in the field, we cannot put a filter in front of the sun, of the incoming light. So it means that we need to find for another way to create filters, how to observe the fluorescence. But luckily, there exists something what is called the natural filters, or what are called the so-called atmospheric windows. And atmospheric windows are specific parts within the radiance along the spectral range, where all the light is being blocked through to the atmosphere, for instance, due to oxygen within the atmosphere or other elements that absorb everything, meaning that there's no light reaching the Earth. Well, and because of that system, so there are these places where there's no light, no radiance reaching the Earth. What is being reflected in those places, then it is assumed, even though it's almost nothing, but that small part where there's no light supposed to be, on those places where something is being back reflected and recorded by an optical sensor, that would be the starting point on how to derive fluorescence. And it's done by comparing on the place where there is no light supposed to be, no radiance, next to where there is supposed to be radiance, and then normalizing that. And based on this normalization, that's how the fluorescence is being retrieved. Now, there exist many fluorescence retrieval methods by now, and here we are not going into detail, but it's always according to the principle of searching for places where there's no light supposed to be, either in oxygen absorption bands or at more narrow scale Fraunhofer lines, and comparing that to where there is reflect light supposed to be, and then normalizing, and then these differences should be related to fluorescence. In any case, the message here is that we have nowadays sensors at different scales, leaf, canopy, landscape scale, and even from the satellite, and they all make use of these principles of fluorescence retrieval. So let's have a talk a little bit about the FLEX mission, the Fluorescence Explorer. FLEX will fly in tandem with Sentinel-3, and that is needed to obtain all the necessary information coming from the Sentinel-3, so about the atmosphere, to do atmospheric correction. Sentinel-3 is an optical mission also, so in this way we can derive the amount of chlorophyll content and leaf area index and all the vegetation properties. And so this FLEX is the Earth Explorer mission that aims to quantify the actual photosynthetic activity of terrestrial ecosystems from space, accounting for vegetation health status and stress conditions. And ESA aims to deliver those fluorescence data, but it's up to the scientists, so up to you and me guys, on how to interpret these data and search for applications or use it for monitoring ways on how to, for instance, to monitor the health or the stress of our croplands. Now, so the principles behind, we have just talked about it, and they are already pretty well understood at the cell level, leaf level, the canopy scale. We are already able to retrieve fluorescence with airborne missions for some specific wavelengths, and nowadays even for the full 2-peak fluorescence profiles. However, how this all works from space is still questionable, since FLEX is not launched yet, will be for 25. And there are still a lot of questions, especially the role of the atmosphere, given that it's such a small signal. So it remains challenging, and we will only know if we can really detect the full fluorescence profile from space once the satellite is launched. Let's have a closer look to how the satellite, the sensors look like. And the sensor within FLEX is called FLORIS. And FLORIS, there are 2 FLORIS sensors, what is called high resolution and low resolution. But don't be mistaken about low resolution. These are hyperspectral missions with hundreds of bands and at spectral nanometer, way smaller than any other existing terrestrial Earth observing hyperspectral mission. We are talking about bandwidths for the high resolution of up to 0.3 nanometer, super narrow, but especially to search for these places where there is no light supposed to be. So where we can track the lights emitted from our planet itself, the fluorescence. So that would be the high resolution sensor that observes in the oxygen absorption band. So where there is no light supposed to be, because it's all absorbed by oxygen or through the atmosphere, and that will be the high resolution. And then the low resolution for us is still 2 nanometer bandwidth, and that region is to detect what we talked before, the so-called MPQ region, so the PRI region, where we can see very small subtle changes into the pigment pool of vegetation as the protective mechanisms when there's an excess of light. So that's the so-called xanthophyll cycle so that we know that also photosynthesis is going on. So we aim with FLEX to measure the PRI region for changes in the pigment pools, the xanthophyll cycle, and we aim to measure fluorescence by detecting the light that is being emitted in the oxygen absorption region, oxygen B and oxygen A. Now, a little bit more technical information. So once the data is being recorded, the radiance, it goes through all kind of processing, but most important is the level 2 processing chain, because there is where the raw radiance data is being converted into physical data that is of interest for us. So after it does an atmospheric correction, and together with the atmospheric correction is the fluorescence retrieval taking place, so that the output will be the fluorescence bands. And based on these, also another output, but not the most important output is the reflectance. And based on reflectance, you can also derive vegetation properties. I think that's the most important for us. And let's have a closer look to the fluorescence retrieval. So basically, it makes use of relative transfer model. Later we will talk more about it, but it aims to derive the fluorescence from the radiance information, but in this oxygen absorption band. So first we have 2 fluorescence data points at 760 and for oxygen B and 687 for oxygen A. Based on these points, we can derive the full fluorescence profile, so that eventually, and that will be the most important product of the FLEX mission, is that the whole fluorescence profile can be given to the community. So we have the fluorescence in the oxygen products. There will also be fluorescence at the peaks, and eventually the totally spectrally integrated fluorescence value. That will be the product given to the community. That will be for 2025, but we already want to prepare ourselves to what can be done with those kind of data. And this brings me to the ongoing study where me and my team, we are working on, is that we aim already to exploit such kind of fluorescence data with existing missions, with relative transfer modeling for the monitoring of vegetation productivity across the world, so GPP, gross primary productivity, or MPP, netto primary productivity. How we do so? These are so-called assimilation systems where all kind of data sources are being combined. And on one hand, we have simulated data. Later, we'll talk more about it with physical models, relative transfer models. On the other hand, we have our satellite data. What we need is both the meteorological data, because we need to know how much light has been coming into the planet, what would be the temperature. All that information is crucial to know how actually the photosynthesis was ongoing. And we need then to have this fluorescence data. For now, we make use of atmospheric missions that also record fluorescence. They are the American NASA OCO2 or GOME satellites. But Europe also has already an atmospheric mission called Sentinel-5 TROPOMI. But it's important to realize that these atmospheric missions, they provide just one fluorescence band. So we do not have the full profile on one hand. And also atmospheric missions, they are very coarse. They provide data in the order of 5 to 10 kilometer pixel resolution. So you cannot have idea of your croplands. It's more to have broad general continental ID. In any case, we started using this data. Then finally, also the field data coming from CO2 flux towers. So that can be used then also for validation or including into the training of assimilation systems. That at these three levels altogether, this data is being combined and is being put into nowadays. Machine learning models are very powerful and popular for it to eventually track vegetation productivity across the world and validating that with those field data. And our focus then is especially on what would be the key information, and we aim to demonstrate that fluorescence, because of its close linkage towards photosynthesis, is actually a key variable in order to obtain accurate productivity information. We all know that productivity is already being provided by satellite missions such as MODIS and so on. But remember, these are just reflectance missions. So they only provide us information about potential photosynthesis based on the greenness, but do not provide information of the actual photosynthesis. So the idea, and we prove that, is that when you include fluorescence, which is this dynamic signal, into your assimilation, into the data processing, we can have more accurate information of the actual productivity. And that's a little bit what these figures are showing, that by including key variables and with fluorescence, sun-induced fluorescence, we obtain more accurate maps of vegetation productivity. So finally, this brings me to this kind of maps that will be produced once FLEX is being launched into this data assimilation. Terrestrial productivity can be more accurately assessed, and more importantly, not just more accurate, but also at a higher spatial resolution as any of the current satellite missions, because of being providing information at 300-meter resolution. So we will have higher accuracy and we will have higher spatial resolution. And further on, we can already also dream further, since FLEX is the experimental mission, scientific mission. If we can prove that fluorescence really becomes a crucial source of information for predicting terrestrial productivity, it is expected that eventually it will become also an operational mission, such as the Sentinels, so that it will be operationally, data will be operationally provided. It will be released to these Sentinel hubs, so that any person in the world can just download this kind of data for anywhere in the world. Finally, this brings me to the conclusions of my first talk. So ESA's Fluorescence Explorer Flex is planned to be launched by 2025. And Flex will be the first global mission that will deliver the full 650 to 800 nanometer fluorescence spectra at 300-meter resolution. Flex will fly in tandem with Sentinel-3 for all the key auxiliary information, so thermal information, optical information. And eventually Flex is a photosynthesis mission, so with applications in global vegetation dynamics, early stress warning, and also improved estimation of the carbon balance. With this, I finished with the first part of the presentation. If there are already questions, maybe it can be asked now, and meanwhile I will prepare my second presentation.
Joe, we can go ahead right now, and
Okay.
you can ask at the end.
Okay, perfect. Yes, let me just one moment open.
I request on online participants, they can put the questions on chat box so that Joe can take directly and answer that later at the end of the session. So thank you. Yeah.
Yes. Okay, one moment. And now I will share. Okay, can you see the screen?
Yeah, we are able to.
Okay. Okay. Good. Okay, so now let's move on a little bit more to the methodological approaches on how to process satellite data. It can also be airborne or drone data, so reflectance data into vegetation products. In this talk, it will no longer be about fluorescence. It will be more about classical reflectance. But we will see a whole diversity of methods for how to process data into vegetation properties, mainly. I focus on vegetation properties, but these methods, also keep in mind, you can also use it for other applications such as water or soil or so on. And let me let's go back to our living planet. So again, the key question is how to quantify vegetation properties based on data that has been remotely detected radiance data, and that we convert to reflectance in this case by means of drones, airborne or satellites. So this actually is is actually that we will learn what are the key processes involved and how we can do this conversion, because it is very important to realize satellites, they do not provide us information about vegetation properties. They even do not provide us this fluorescence. At the end, satellite data, or any kind of sensor data, they provide us digital numbers that then can be converted to radiance data. And radiance data, that's the starting point, can then be converted to reflectance data. And based on reflectance data, we can derive properties of our vegetation. Radiance data, it comes from the solar radiation that interacts with our Earth. So it interacts with vegetation. There's always three mechanisms going on. On one hand, vegetation reflects part of it, reflects to the sensor, but also vegetation absorbs for photosynthesis. And within vegetation, there's also scattering taking place, right? So the photons, they are being scattered throughout the canopy and the atmosphere and so on. So eventually what we observe is reflected radiance that can be converted to reflectance. And let me show the laser pointer. So that would be how, when it's converted to reflectance, how reflectance would look like. And based on this, we try to having some knowledge on what actually was happening with these interactions. We try to model these interactions that we can eventually. My presentation is again. Okay, I need to be careful. I need to have a better computer. So eventually, with these interactions, is that we try to obtain information of vegetation at the cell scale, leaf scale, canopy scale, and ecosystem scale. Now, how exactly does that work? So let's have first a closer look to how reflectance look like. You may have seen maybe this figure before in other presentations, because it's a classical figure of a vegetation spectrum where most of the light is being absorbed by the pigments, so very low reflectance. And the subtle variations that we see here are due to pigments, mainly chlorophylls, but also these carotenoids, anthocyanins, this xanthophyll cycle I was talking before, that is in this region taking place. Then when we move to the red edge, where vegetation is no longer, where light is no longer being absorbed by vegetation, then we have these scattering mechanisms due to the canopy structure. So that's why this region can be used for quantifying more structural properties such as leaf area index, biomass, plant density. Then there are also absorption regions due to water content available within the vegetation. So these are specific absorption features that we then can use to derive information about water content. And finally, when we move more towards the shortwave infrared, the SWIR, here we will see absorption feature due to the woody material, so lignin, cellulose, senescent material. That region can be used for detecting those properties. And this figure also tries to highlight the importance of hyperspectral sensing, because when we do more classical broadband sensors such as Sentinel-2, and that would be the black lines, you would miss all these specific absorption features. Sentinel-2 is great for estimating chlorophyll content, for instance, because it has enough bands in the visible part. Also for leaf area index, because there are enough bands in the near infrared. But for instance, for water content or for this woody material, it does not have the proper bands to detect these subtle absorption features. A quick overview of hyperspectral satellite missions, as those are the key missions needed for quantifying all those vegetation properties. And we have DAISIS, which is a German mission that's within the International Space Station mounted. Only this mission goes up, well, this sensor only goes up to 1000 nanometer. But more interesting are these new generation imaging spectrometer missions that are satellites and covering the globe. One was recently, well, a few years ago, launched by the Italians, Prisma. And the other one was recently also launched by the Germans called ENMAP. Both of them, they cover the full 400 to 2500 nanometer spectral range. And so they have over 100 bands, and they have a spatial resolution of 30 meters. It's just important to realize that these are technology demonstrators, so similar as our FLEX mission. They are more to show the capability of imaging spectroscopy with the idea that eventually it pushes science and technology forward, because nowadays, both the European Space Agency, ESA, as well the Americans, NASA, they're both developing operational imaging spectrometer missions. So same as the Sentinels or ASMODIS or Landsats, but then again also over the full 400 to 2500 nanometer region with over 200 bands. The spatial resolution, CHIMER, it will be at spatial resolution at 30 meters, and SBG, soil biology, geology, also at 30 or 45 meters. And these missions are supposed to be launched in the upcoming years. Oh, and here we have some information about our mission FLEX again. And so, yeah, so just a few more words or some illustration about this Prisma and ENMA missions. So these were the pioneers for us in imaging spectroscopy technology. You can download these kind of images, but you need to request that they acquire these data over specific regions. So it's not yet like Sentinels that you can just download it from a hub for any place in the world. And both us and I understood also Indian colleagues, they were also already exploring this data for specific applications. And more of interest are these upcoming European mission CHIME, Copernicus Hyperspectral Imaging Mission for the Environment, that will be operational just like any of the other Sentinel-2 missions. And here we see again FLEX as our own satellite mission. So this gives us set a scene, and this gives us an overview of what we can do, what we have. We have all these satellite missions, and they can observe from local to up to the whole globe. And that data eventually we can use for all kinds of applications, crop yield, biomass, leaf area coverage, chlorophyll, fractional vegetation cover. But how to do so? That remains the main problem, how to convert raw data, radiance data into applications. And to do that, well, the key always is that there is a model is required, a model that converts your input data into your variable of interest. So the objective is how to transform measurements into biophysical parameters, estimates, data. Very simple. It's always our spectral data on one hand, and also you will need field data for validation. And you may also want to make use of simulated data of these relative transfer models. So our outputs are our biophysical variables. So now entering into the methods and models, basically there are two types of methods that we can think of. On one hand, we can think of statistical methods. So we just have our data and we try to come up with correlations or regressions also. Or on the other hand, we can try to go for a more physical approach by trying to understand and track and simulate or approximate all the mechanisms that have been taken place between the reflected the radiance data and the interaction with vegetation. So that would be through radiative transfer models, RTMs. In the RTMs, we can use that to make simulations of how reflectance would look like. For instance, for the design of new satellite missions, for retrieval approaches, so mapping approaches, or maybe you want to evaluate a new kind of vegetation indices. So you can make use of the simulated data to evaluate or to come up with new kind of retrieval methods, such as spectral indices. Methods, there are tons of methods have been published in the literature. You may be familiar, for instance, with vegetation indices. And here I just list a few of them. Later we go into details, but starting from very simple vegetation indices, you just take two spectral bands, you calculate an NDVI and try to link that to chlorophyll, for instance. Red edge indices, so that this red edge is the inflection points between the visible and the near infrared, and that also can be dynamic, so you can relate that to chlorophyll content. So derivatives, integrals, continuum removal, wavelets, and then we start to enter into the more non-parametric measures, so the data-driven methods, such as principal component regression, partial square regression, ridge regression, and moving further to machine learning methods, random forest, neural network, support vector regression, Gaussian process regression. And then finally, these methods are making use of this relative transfer modeling. We can apply inversion. Later, we will talk more about it, either through numerical inversion or through lookup table-based inversion. In any case, first, let's start a little bit simple, and let's have a look to the terminology. So we always have a model to convert raw data into a product of interest. We have either statistical models or physical models, that is inversion of these physical models. When we focus on statistical models, that can be parametric regression models. We parameterize ourselves the model. So we select ourselves the bands, we give ourselves the equation, we select ourselves a fitting function. And on the other hand, non-parametric regression models, where we don't parameterize, but it's being parameterized by the algorithm itself. For instance, neural networks or so. So these are the data-driven methods, and that can be either through linear transformations of the data or non-linear transformations of the data. Linear, you can think of applying a principal component analysis. So it converts the data into linear components. And then you apply a regression model. While with non-linear transformations, you can think of all these machine learning methods that search in a flexible and adaptive way for relationships. So I think this is what I was just talking about. So we have statistical methods, either parametric, that relies on some physical knowledge, because we as the user, we define ourselves the equation, and we do that with some knowledge. The NDVI, why is that? Because of the high absorbance in the red and high reflectance in the near infrared. So it has some physical knowledge that you introduce yourself into the equation. On the other hand, the non-parametric methods, these are the data-driven methods. So it's just based on the data that it tries to search for relationships between input and output. Then we have the physical methods, and they try to run these relative transfer models and then calculate backwards to the variables of interest. So those make use of cause-effect relationships. And then finally, we'll talk later more about it, hybrid methods. And hybrid methods tries to combine the best of the physical methods together with the best of the statistical methods. To give you an overview for a better understanding, parametric regression, we parameterize ourselves, we put the equation into it, for instance, NDVI, and we put our fitting function, for instance, a linear regression into it to obtain a model towards our variable of interest. Non-parametric regression, data-driven. We just put in all the data into an algorithm. It searches for relationships. Here, neural networks is perfect regression and gives us an output. Relative transfer model inversion, it simulates the vegetation, how reality would look like, and then we try to calculate backwards towards the variables of interest. Later we talk more. And then the hybrid, so we combine the non-parametric methods for model developing together with inputs from the relative transfer models for simulations. So 4 ways how we can obtain the same kind of products. First, now let's go more into details about the statistical methods, which is the large majority of methods being used. And they are just interested, or they just give us information if there is a relationship, but we do not know why there is a relationship. It doesn't go into the underlying mechanisms, right? But these are perfectly fine to tell us that they are, if they are as indicators of our vegetation products. Only with vegetation indices, we need to be very careful, because as they just try to come up with simple relationship, there are all kind of so-called confounding factors that may influence these relationships and may give us biased information, or may it doesn't take into account loads of factors that are also playing a role, right? Which makes that vegetation indices relationships, they may work fine on one place or within the lab, but when you move them to another place, because it doesn't take the whole picture into account, they lack generality, and you cannot be sure that a relationship that you measured in the lab will work equally well in the fields, because of the field is more heterogeneous, it's another time of the year, and so on and so on. So far, I talk about vegetation indices. Note about all the other statistical methods that are maybe more powerful. We'll talk more about it at these non-parametric methods. So just a short overview of some vegetation indices. We can summarize them as 2-band indices, 3-band indices, 4-band indices. So over time, indices, more complex indices have been developed that try to be more robust towards confounding factors such as soil influence or other influences. And that would be just the vegetation indices. But when we move towards hyperspectral data, it doesn't make sense just to rely on 2 bands when you have hundreds of bands available. So instead, more of the shape of the profiles are being used, for instance, to derive the red edge position. But maybe more interesting is to calculate derivatives over the hyperspectral data or integrals over a region, and use that information then to the variable of interest. Another popular method, continuum removal. So it takes the general shape, and then these differences, these absorbance, that information is then used to link towards variable of interest. Wavelets is to search for small patterns within the spectral data that again try to use that to link towards variable of interest. Let's have a quick overview of the strengths and weaknesses of these parametric regression. Well, strengths are obvious. These are simple methods, so they are comprehensive. Little knowledge is required. You can just calculate the NDVI, link that to, for instance, chlorophyll content, and you have a simple model. Very fast in processing, so it's a perfect first approach to see if any meaningful maps are appearing. And it's also computationally inexpensive, so anyone can do it. Even on your mobile phone, you could process this. However, there are many weaknesses. So, and especially when moving towards hyperspectral data, it makes only poorly use of the available information within the spectral information. And so at best, only a spectral subset is being used. And therefore, there's a risk to be more noise sensitive compared to full spectrum methods. Also, parametric regression, you have boundary conditions because you parameterize yourself the method with the risk that maybe that index that you were using or the equation is not the best one, right? So you never know if you are actually having it fully optimized. Yes, with statistical functions, these kind of methods, you can focus only on one variable at a time. Meanwhile, some non-parametric methods, they can predict immediately a whole range of variables, such as neural networks, for instance. And then there is maybe the key is this limited portability. It may be successful on one place, but you do not know if it's successful in another place. And also crucial to me, it doesn't provide uncertainty estimates. Later we will see more, but with uncertainty estimates, we mean that we have additional information about the quality of our model. And with simple equations, we do not know, and we just get our outputs. So, okay, finally, parametric regression, how to apply, very easy. So we have some data collected in the field, typically some variables, chlorophyll, LAI. We have associated spectral data, either from a spectrometer or from satellites, just the pixels with the GPS coordinates. So, and we use that for calibration of our indices and validation. And once we are happy with the validation, you apply it to an image, you apply the index that has been calibrated and validated, and eventually you get your output map. Very simple, easy to use. Now, let's move on to the non-parametric models. These are these data-driven models, so no explicit feature relationships. And let's first start with the linear non-parametric models that can be stepwise multiple linear regression, principal component regression, partially square regression, weight regression, lasso. Basically, all these methods, they compress somehow the data into components, for instance. So they compress it and then at the end come up with a linear relationship towards your variable of interest. PLSR already takes relationships of the variable into account, meanwhile PCR just compresses the spectral data and then makes a linear relationship. So they are slightly, you can have slightly more advanced, but the key message is they just make use of linear transformations. And yes, if my computer is responding, right. And then we also have the second part of non-parametric models, the non-linear models, which became much more powerful the last few decades. These are the so-called machine learning methods. We can think of decision trees, support vector regressions, Gaussian process regressions, all kind of neural networks, kernel-rich regression, Gaussian process regressions, and there are many more. And let's have a look to one specific method, which I like a lot, is these Gaussian processes, because that's a so-called probabilistic or Bayesian method. And with that, we mean that it doesn't provide us just an estimate, but basically it provides us a probabilistic output. So a whole a Gaussian function, meaning that we have the mean estimate, but also we have the standard deviation of it. Gaussian processes is from the familiarity of the so-called kernel-based methods, so similar as support vector machines or also like neural networks. But the advantage of it needs only few data points, basically, and for providing very good results. So it's simpler than neural networks with fewer sample points. And what I said before, it doesn't only provide the mean prediction, but also the estimates with it. And also of interest is that it provides band ranking. So we know, we have an idea of the the relevance of the input bands. So this way we can immediately see what are the sensitive bands of the model. And now I realize you were not seeing the laser pointer before, probably. So I hope now you can see it. And here is an example of Gaussian processes that we applied to over an agriculture area. So we have a satellite image, we trained and tested and validated, and then eventually applied it. And what I want to show you is so this is just the RGB, the input. The output, on one hand, we have, in this case, this is chlorophyll content. So we have an estimate as output, but also it provides these standard deviation, so the uncertainty. And this, I think, is relevant because, for instance, we have these very nice estimates of high chlorophyll content over an irrigated area, but we can see that there's a specific zone with high uncertainties. Now, have anybody an idea what is going on? Basically, what it says is that, look, I provide you an estimate, and it looks reasonable when you see it, the irrigated circle as a whole, but I'm not that certain about it. And what is happening? It appears that we have the field that actually it was just irrigated, so the soil is more wet, is darker. So basically, it says my model can give you an estimate, but something happened, something I'm not being familiar with it, I was not trained with, so that's why I give you a higher uncertainty for that region. So that's excellent, because that's information that we want to know, to have. Basically, it can decide us to go back into the field, collect more data over this region when it was just irrigated, so also with a darker soil, right? So with these uncertainties, we can know where the model is doing well and where the model is not certain about. So this also gives me to an overview of the strengths and weaknesses of non-parametric regression. So one of the main strengths is it's a fill spectral method, and there's no need to decide yourself of selecting certain bands. You can throw in all the spectral bands into the algorithm. Maybe you want to combine it with a dimensionality reduction method such as PCA to squeeze it into a few components. But the key is that you can make use of the complete spectral information. It's advanced, adaptive, it can create nonlinear relationships. And typically, it provides more accurate and robust performances than the parametric or the linear non-parametric methods. Some of these machine learning regression algorithms, they cope well with data sets showing redundancy and high noise levels, meaning that they can be robust. And a main advantage, once it's trained, you can apply to the image and you immediately have your output. Some of these methods, like especially neural networks, can be trained with a very high number of samples, so over millions even. Some of these machine learning may provide insights in model development, such as Gaussian processes, which provides us information of what are the relevant bands. Also, decision trees also provide us information about relevant bands and how the tree is looking like. And some of them, they provide multiple outputs, such as neural networks, and we can train that immediately provides us estimates of, for instance, LAI and chlorophyll together. And some of them, and I think that's key, they also provide these uncertainties, as what we just talked before. However, there are also some weaknesses. They are computationally expensive in the training, especially. And hyper-complex models can be generated, which means that often it's trained very well, but then when you apply to another place, it doesn't generalize so well. And this is a typical problem of overfitting. And to avoid that, it's always important you apply independent validation and never rely just on your training results. Always only trust your validation results and have a look to the maps also. So these algorithms, they can be difficult. Some of them are with a higher number of samples. Yes, for instance, Gaussian processes can only deal with a few thousands of samples maximum. And a key weakness maybe is that expert knowledge is required. But here I want to make a point that the software we and other people developed make it easy. That nowadays you can select just libraries and packages or even graphical user interface software that does the job for you. It does the training, the tuning, just provides you the results. Yes, and another weakness is that these methods are considered as black boxes. So it's no longer with a physical meaning. It's just a powerful model, but we don't know too well what's going inside. And yes, this we already said that sometimes the training doesn't guarantee that it also will applicable to other places. So how to apply it? It's the same as before, but actually now it's even simpler as before with the spectral indices, because we can skip this step of band selection and transformation. Since it's data driven, we just throw in our training data. We have some data for validation. It trains and we select the best validated model. We apply that to our satellite data and we get our output of interest. So keep that in mind, that actually vegetation indices is a more complex approach when you aim to optimize, because you never know, you make use of the best bands, the best fitting function, as compared to non-parametric regression models, right? So with data-driven methods, you just throw the data in, it does the job for you. Only what you have to do is to compare different algorithms and make sure you validate and then apply it to your image of interest. Now let's move to the physical interpretation of remote sensing data. So by making use of these so-called RTMs, relative transfer models, that describe the interactions between remote sensing data, reflectance or radiance, with key variables, state variables, and these are the variables that have a direct influence on the shape of the reflectance. So that can be chlorophyll content that absorbs the reflected light, can be structural variables such as leaf area index with the scattering that changes the shape of the reflectance. So those are the relative transfer state variables, and based on these variables, maybe these have direct relationship, but based on these variables, you can also come up to indirect relationships, which are maybe not observed in the directly to the reflectance, but there exist relationships. And here you can think, for instance, to nitrogen content. Nitrogen content is related to chlorophyll content, and chlorophyll content is the variable that changes the shape in the reflectance. So there are some variables of interest. Also, we can categorize these RTMs into what we call economically invertible models. So these are simple models with just a few variables that allow us to invert, to calculate backwards. Or on the other hand, we also have the non-economically invertible models. And these are very complex, advanced models that are maybe not applicable for doing inversion, but they are excellent for generating accurate scenes. So they have good understanding about the relative transfer within the canopy and so on, because they are able to be super realistic. And you can create your trees, your crops in just exactly the same way as it would look like in reality. But that takes a lot of computational and rendering time, meaning that you cannot generate many scenes of it. Yes, we've seen this figure before, but now let's move a little bit more into these RTMs. We can use it for all kinds of applications. We can simulate, make our own simulations, and, for instance, develop new indices or evaluate it. We can use it for mapping applications, and we use RTMs a lot for instance, the development of the FLEX mission is based on simulations. That counts for any mission, by the way, that we use. We first simulate how a satellite would observe the Earth thanks to these RTMs. So these RTMs, we have them at various scales also, leaf, canopy, and also atmosphere. I will only focus on leaf and canopy. And there exist all kinds of RTMs in a very simple way towards very advanced way. In the most simple way, a leaf would be approximated just as some layers, and these layers, they have the properties of chlorophyll absorbance, water content absorbance. So when there are more layers introduced, there would be more chlorophyll absorbance. And so with just a few variables, we can describe how reflectance and transmittance would look like. But there also exist more complex leaf RTMs that really try to simulate all these single cells within a leaf and then do the light propagation through it. But again, these are complex models where you cannot generate many simulations. Same is true for canopy models. So yeah, in a very simple way, leaves would be just be stacked in a random way in an infinite area in what we call a turbid medium. And then the leaves are you can define the density of the leaves as leaf area index and the leaf angle distribution, but that's it. The more complex models, they take into account geometry in a simple way as geometric envelopes, and then it moved towards hybrid methods, so that combine both of these towards eventually as a Lego style way that you can build up your own surface and give the properties to each of these cells or volumetric cells, voxels. So again, a leaf, it's key to realize that a leaf is not opaque, but transmits. There's always flowing light through the leaves. So we need always to have reflectance on one hand, absorbance, what is being absorbed by the cells and the chlorophyll pigments and other pigments inside, and transmittance eventually. So that would be a more advanced model. This would be a simple model that describes a leaf just as a number of layers, and each of these layers, they have as some absorbance properties based on water content and chlorophyll and dry matter. Canopy models, you can also see how they evolved over time from very simple illustration of canopies towards realistic rendering of, well, this would be weed scenes or forests, first with these geometric envelopes. But even nowadays with computer graphics, you can render super realistic scenes. Then the light is propagated through it for any wavelengths, so that by this way you have the reflectance for realistic simulated scenes. Very nice. It gives you good understanding of how light interacts with vegetation, but for mapping applications coming from satellite data, those kind of simulations are less useful. The most useful canopy model is the sail model because of its simplicity. Basically, this model just needs to know where the sun is located, needs to know where the sensor is located. It calculates then the reflectance towards the sensor or the hemispherical reflectance. And the canopy is just described as these elements of leaves that are scattered in there. And you only need to know the density of the leaves and the orientation of the leaves. You need to know some information of the soil. and that's basically how these models, so they became more advanced, so to say. In this case, you have additional information of what kind of soil profiles and the structural geometry. Another model made use of sail that added also a soil model. And nowadays, based on sail, the scope model, that would be the most advanced because it also, we move towards being super realistic in structure. At the end, that's not that useful for satellite application. We instead, at least for us, the fluorescence community, we rather move to integrate also photosynthesis models, so that also we can obtain information about how well the plants are photosynthesizing, fluorescence that is being released. So that became part of the models. Fluorescence, the biochemistry model is within the leaf model is within the canopy model. You can link that also with atmosphere model, so that eventually you can trace the whole energy balance of the photosynthesis, scattering, absorbance, and so on within leaf and canopy and atmosphere. The scope model we use heavily within the FLEX mission. Yeah, some words about ray tracing. So these most advanced models, they make use of the ray tracing approach. And similar as how does it work, ray tracing? So as this, we have this medieval painting where this guy, the painter, was using this gridded canvas and then started painting cell by cell. So he was actually observing what he saw of the lady for a single cell that he then started painting in his place. So basically, you trace each single light source. The ray tracing models do exactly the same. They trace how the photos interact one by one, and for every specific wavelength. They are, so in this way you can render very accurate scenes, but again, it takes a long of time. A hybrid ray tracing model would be Flight, where it does this ray tracing, but it simplifies the canopy by this geometric envelope, so to keep it still fast and comprehensive. Okay, so far we were talking about, I was using some words such as backwards and simulations, and basically we can distinguish between what we call forwards, means that we do some simulations with these RTMs based on some input. So we give some leaf chlorophyll and canopy leaf area index, and we give some soil reflectance, and we tell where the sun is located. And we add additional reflectance for the soil maybe or so. We put that into the RTM and we let it run. So we let it run, that it provides our radiometric information that can be reflectance or radiance. That would be forward, from input towards output. For mapping application, more of interest are the backwards. And with backwards, what we mean is that we have our radiometric information coming from our satellite, the reflectance data that is being recorded, so a single pixel, so to say. And from this single pixel, we try to calculate backwards how that would lead towards our input variables of the RTM, the chlorophyll, the LAI. And how to do it so is by linking for every single pixel against all the possible simulations until it finds a perfect match, so that we have the closest approximation of simulated data, I would say, against the reflectance of a single pixel. Once we have done that, we know it's for certain chlorophyll, certain LAI. We put that information into the pixel, move to the next pixel, and so on and so on. So eventually, that's what we do backward, or that would be the inversion of an RTM. Of course, you try to also add some a priori information, because you don't want to do simulations of all possible possibilities. You know where the sun is located. You may know some limits of how much, for instance, leaf area index or chlorophyll content the plant typically has. So you can narrow the boundaries, but still you do your simulations within some certain ranges to search for a spectral match, so that you obtain eventually a certain chlorophyll or LAI or so on. So in practice, you can see the scheme is a little bit more complex to do that. So we have our RTM, we have some input data, we make simulations, what we call lookup table, and we make a large number of simulations, and within these simulations, we can use that for applying our inversion. So we search for spectral match within these simulations for each single pixel. Then when we found the best spectral match, of course, we can add some additional information for calibration, and we validate. If the validation is okay, that's a strategy, that scheme, we can then apply to the whole image to eventually obtain our vegetation products. So that would be the physical way of obtaining vegetation products. The advantage of this method is that we could actually, it's always good to do validation, but in case you have no data at all, you could just run your simulated data over your image so that you can obtain a map even without having any additional information available. However, it's never recommended, because you should always validate your products. So strengths, again, it's a full spectrum method. It has a reputation of it's physically based. So this is no statistical data-driven methods. It's purely based on light interactions. And this is, for instance, how the MODIS vegetation products work. So because it can be globally applicable, you can apply it to any pixel, any reflectance that's observed over the world. It can provide multiple outputs. So all the RTM inputs, that will be your outputs. And also you have uncertainty information, because you have information how well the spectral match was working. So you know for each pixel, was the RTM able to identify the input variables with good accuracy, with high spectral match or not. Weaknesses, so this is a computationally demanding method, and it's therefore not really recommended for operational approaches. Also, it depends on the quality of the RTM. Of course, if the RTM is not really realistic, your output will also not be realistic. It's a quite complex approach. We've seen it requires many steps. And also you are also limited by your boundary conditions. No, what would be your upper and lower value of your variables? You typically introduce all kind of limitations. Some variables you keep fixed or so you also constrain it, which impose limitations. And also it has influence of noise, because at the end we rely on simulations which are over vegetation, but many pixels are non-vegetated or partly vegetated. So, and for these pixels, the model is not so well prepared for it. So you also include some uncertainties. And then finally, and that's maybe then the most interesting way, are the hybrid methods. And here we use the same principle of the physical way, is that we generate synthetic data and we make simulations, right? So we have our lookup table, but instead of searching for the best spectral match, we use these simulations for training machine learning methods like Gaussian processes, neural networks or so. Of course, we always again validate it against independent data. But in this way, we just train it one time. And once the model has been properly validated, you apply it to an image and you have immediately, again, your map of outputs. And this is a very powerful way because we can be as generic as we want. So we can make models that are applicable all over the world. It is very flexible because of the power of the machine learning algorithms. With good validation, it gives also very good results. And this is the way how space agencies nowadays come up with their models for generating vegetation products. So again, so the strengths and weaknesses of hybrid methods, we have all these strengths of the machine learning and the physical way methods. However, there are also some weaknesses, as like that it can be training computationally expensive, hyper complex models can be generated. So this gives again the weaknesses of the machine learning methods that also you need to take that into account. But I want to give you an example of, we are currently developing the models for the operational hyperspectral mission CHIME. So we are developing hybrid models, for instance, for mapping and monitoring crop nitrogen content. In this way is that we use simulations from relative transfer models. We optimize our simulations with some methods such as active learning, and also we, because these hyperspectral data often is redundant, we squeeze it, we compress it with principal components into components so that there's no problem of that the models become too heavy and we are running into computational problems. But in any case, the point is that we use simulated data for training, we validate it with campaigns, and eventually this leads to good maps and are generally applicable. Okay, the general overview to close this part is that just for you guys to understand that they are parametric regression models. You parameterize yourself, your equations, and you choose your vegetation index or other type of index. You choose your fitting function, for instance, linear regression. On the other hand, they are non-parametric methods, the data-driven methods, where you can either use all bands or you make a selection or you compress, apply transformation into lower dimensional features such as PCA. So this would be, and then you apply non-parametric regression methods, for instance, machine learning methods. We have the physical methods. Typically, you make use of simulations, RTMs, either by creating a lookup table. So you first do simulations, or you let the RTM running for each pixel until you find a perfect spectral match, search for spectral fitting through a cost function. And then finally, we have the hybrid methods, where we combine the RTMs together with the machine learning methods. And I did here this example. I was each time using exactly the same input. Each time I was evaluating the best possible method for parametric regression, non-parametric regression, RTM, and hybrid. And it generated me an output map. And you can see that it's the same variable. The maps, they look different. And for me here, this is the key message also. Be always careful with the methods that you are using, because the method determines your output map. And even though you may have good accuracy, Of course, your validation are always just a few pixels. It's never the complete map. And you can see that depending on the method you are using, you will have different types of outputs. It's always important to go for the best possible methods and take into account the results of the map as a whole and not just your validation points. And here, for instance, uncertainties are playing a very important role, because then you can see per pixel what is the quality of your model. Just a taxonomy so that you have the broader picture. We focus on retrieval. We have you can have either regression or the inversion. Regression can be parametric, non-parametric. You have the indices, shape indices, and so on. Non-parametric can be either linear transformations, such as partially square regression, or non-linear. These are the machine learning, decision trees, neural networks, kernel-based methods. RTM, either you create a lookup table, you create your simulation before, or you let it run per pixel. And most interesting probably are the hybrids, which combines the RTM with the non-linear, non-parametric methods. So being aware of all these methods, that this would bring us now to the following questions. Now, once you want to apply it, what would be your best method for your specific application? Because there are all kinds of questions now arise. What would be the band combination formulation? What kind of fitting function? When you go for statistical methods, should I go for parametric or non-parametric methods? What would be training data, validation data? If you go for physical methods, what kind of fitting functions should I use? How to parameterize my RTMs? Do I have any a priori information to narrow down my simulations? Are there regularization options? And all these questions, each time they appear over and over again for any kind of application, any kind of variable, any kind of mission, any kind of sensor you are using. So this makes that retrieval of vegetation properties, or just the processing of satellite data in general, is challenging, and is a bit of an art. You need to have some feeling of these methods to make the right decision to come up to your best possible maps. Now, the good news is that we have developed software that does all this job for you, so that you can run all these possible combinations and then decide yourself what would be the best possible solution. And now the remainder part of my presentation, I will talk about this software that you are familiar with it. So it's called Artmo, and there is a website for it. And within this Artmo, we have collected all possible leaf models that are publicly available in the world, all possible canopy models that are available, also combined models, even the atmosphere models are also, you have access to it. We developed all kinds of retrieval toolboxes. So for the indices, inversion, machine learning. Within the machine learning, all kinds of further options are also available. And we developed several tools. And now I will just go a little bit into detail about all these options, just for you to be familiar, that you have some feeling and understanding what can be done. Basically, the background for developing this tool was that when I did my PhD now over 15 years ago, at that time, there were these RTMs available, but we never knew what would be the best RTM for your own application. Also, these RTMs, they were not just publicly available. You had to contact, and people were just using just the RTM that they had within their lab with a different programming language or so. And there were no GUIs at that time available. If there were, they were just for doing some forward simulations, but not for mapping applications. So we felt there was a need to come up with a overarching software framework that brings all these RTMs together, standardize them. Once you know using one, you can use all of them, and also focus on that they become practical, that you can have some, that you have the tools in hands for running them for your specific applications, such as mapping applications or others. So we aim to develop back in 2010 a graphical user interface toolbox that operates various RTMs in an intuitive interface, provides comprehensive visualization, can be run for multiple and hyperspectral data. So the key is you can retrieve your biophysical parameters with all these methods we just discussed before. And you can even take into account different land cover classes. So for instance, for grasslands, you want to make use of a simple RTM, but maybe when then you also want to process forest, you want to make use of a 3D RTM. That's all possible. It's called ArtMo, Automated Strategy Transfer Models Operator. It's supposed to be plug and play. Installation is a little bit of effort, but once you have installed it, you just type ArtMo within MATLAB and it will be open. So it's a very easy way then afterwards to operate it. Supposed to be intuitive. Once you know how one RTM works, you can make use of all of them. Supposed to be robust, although we keep on improving it, and users sometimes come up with bugs, and then we try to fix it. And in this way, thanks to the user community, it becomes more robust day by day. And generic, you can apply it for multispectral data, hyperspectral data, drone, airborne, satellite, doesn't matter. And maybe just a few words about why we developed it in MATLAB. It's because of the RTMs were originally developed in MATLAB. So the leaf models and the canopy models, most of them were given in MATLAB. We also, underneath, all the data is being stored into SQL data servers, MySQL we chose. So any simulation, any result you do, it always is stored within the service. You can always get it back. So in an easy way, you can it keeps the data in an organized way stored. In the image format, we started with hyperspectral data. We mostly use NV software, but it can also process TIFF formats. And yes, and back in that time, 2010, now this is super common or normal. But at that time, back in 2010, the apps were emerging, and that was really exciting to think in the same way for remote sensing applications, because as scientists, we were publishing a lot, but the methods were often not well shared at that time. So we thought that together with all the methods that exist in publications, we should come up with small apps that then can be implemented into these toolboxes so that not only RTMs are in there, but also methods, like the retrieval methods or classification, unmixing, and so on. So that was a bit the philosophy at that time, to bring it all together. Nowadays, with HIT and it's common practice, but in that time it was quite some efforts to focus on methods and put them into graphical user interface that they are easy to use. So this is how ArtMo would look like schematically. We have the leaf models, we have the canopy models, and we have the retrieval, so the mapping toolboxes, classification toolboxes, and all kind of tools. And just maybe now a few words of the what we've seen before. So the lookup table-based inversion toolbox. Each of these toolboxes, they look in exactly the same way. So you need to go through input for your training data or your lookup table data or your spectral index data, and you need to decide on your settings what kind of algorithm you want to use, or lookup table inversion strategy or spectral indices. Again, it evaluates against your validation data, your results, and you just apply, for instance, the best performing algorithm in the retrieval step towards your image, so that you eventually get your map of interest. So also here, once you know one toolbox, you can make use of all of them. That time we published a paper where we compared all possible indices, all possible machine learning, all possible inversion strategies. We showed the maps of the best performing one, the map leaf area index for vegetation indices, Gaussian processes plus uncertainties, absolute and relative uncertainties, inversion, plus the residuals, which are also uncertainties, so tells us about the performance of the inversion. And here again, the point is that depending on the method you use, you get a different type of map. So here I really want to insist, be careful what method you use. Try to go for the best performing one, giving the highest validation results, also that have good uncertainties, and take also mapping speed into account. Of course, indices are very fast. Inversion takes a long time. I would say hybrid or machine learning methods are the best in between compromise methods, being in performance and in speed. Finally, maybe when moving now towards operational processing, so when we aim to process the whole world, so to say, we need to think of these methods, know about their qualities, their properties, and so you can categorize these methods for certain qualities, such as the generalization capacity, mapping speed, uncertainties, the accuracy, variables. Well, let's have a look to parametric models, the vegetation indices, for instance. They are very poor in generalization capacity. What I said before, you may have good results on one place, but no guarantee it also works equally well on another place. But they are very fast, so here they are very strong. They don't provide uncertainties. Results can be good, and you can do it for any variables. That's also a strength. Now, the non-parametric methods, generalization capacity, they are typically more powerful, so they can easier be applied to other places. Mapping speed, very fast, but they have these advantages that, especially these Gaussian processes, you can provide uncertainties. They are the most accurate methods, and you can also apply it for any variable. Now, the physical methods, they have the best generalization capacity, and you can apply the RTMs because they're according to the physical principles anywhere in the world, but they're very slow. They can provide uncertainties in terms of residuals. Accuracy, typically they are not so flexible as machine learning methods. Variables, you are restricted to the input variables of the RTMs. Altogether, the hybrid methods that combines RTMs with non-parametric methods, they offer the most properties that we are looking for. So it can be generally applicable all over the world. It is fast, it provides uncertainties, and can lead to high accuracies, and you can apply it for all the variables that the RTMs offer. So hybrid methods for us is the winner for moving towards operational processing. And that's what we do now for the CHIME mission, the Copernicus Hyperspectral mission. We develop the vegetation products. So most important of these missions are the reflectance, obviously, but also ESA asked for the development of higher level products. So and for me, it's the vegetation products, so level 2B products. And that's what we do. We train models. We take into account the dimensionality of the spectral data, because too many bands hampers the accuracy of the machine learning methods. So you want to either you take a subset of your bands, or you squeeze them, you convert them into components with dimensionality reductions, such as PCA. That's what we do here. And we did some tests. PCA typically outperforms when you use all the bands, or when you take just a subset of bands. So we have the spectral data compressed, and then also in the sampling domain, because with RTMs you can simulate millions of simulations. There exist methods, it's called active learning, that selects for you the most relevant simulations, and that also, so we applied, and so in this way also the accuracy is improved by selecting only the relevant simulations in comparison to when you would take all the simulations. So in this way, we have a workflow developed using RTMs, active learning, dimensionality reduction. We train our machine learning algorithms. We validate it against campaign data and simulated data. Well, any data that we find, we apply it to existing satellite images, such as Prisma or Nmap, so hyperspectral. If everything works fine, and so this is the current status of these models, eventually we propose them to ESA as applicable models for operational processing of vegetation properties. And here is one example, for instance, of canopy nitrogen content for space. I believe this was the first nitrogen map from hyperspectral data. And you can see the high accuracy, because it's not classification, it gives you the estimates. By the way, this is over Europe. This is Munich in Germany. Here, this is the airport of Munich. So no vegetation, no nitrogen. These are some lakes, and these are highly intensive agricultural lands with high nitrogen content. Here is a river. That's also always productive. So with a lot of vegetation next to the river, the map seems to make sense. This is a forest, but not only that, we also have the uncertainties. So the higher, the more uncertain, or the lower, the better the quality. And you can use uncertainty as a mask in case you want to only give you the nitrogen values that fall within an uncertainty below 20%. And this would be like a reliable map of nitrogen content. Apart from the retrieval, there are also some tools in Atmo. You can apply spectral, there's a sensor tool that you can define your sensor band settings. And based on that, you can apply spectral resampling so that you can convert your data, hyperspectral data, for instance, from one sensor to another sensor. And that's always needed, so that you need to make sure that spectral data matches of your training data, validation data, your image data. Emulation provides statistical methods to approximate the functioning of relative transfer models that are typically computationally expensive. So for instance, atmosphere models such as Motran or these 3D models, they take a lot of computational power. With emulation, the idea is that we develop a statistical method, a model that does exactly the same as your original RTM. With the advantage, once it's trained, training takes a lot of time, but once it's trained, you have immediately your output, what normally the physical model would take you a long time. So you accelerate, you speed a lot up, and you can use it then for applications of converting, for instance, multispectral data into hyperspectral data. You can develop an emulator that converts a Sentinel-2 image, in this case, into a hyperspectral image. Finally, global sensitivity analysis. These RTMs, again, you can calculate the relative contribution of your input variables, so chlorophyll content, the water content, so that you have an idea what are the driving variables of your RTM. So we see a dark green is chlorophyll content is mostly driving the visible reflectance. And so basically, these are small tools that gives you information. What are your driving variables? Also, this is outside Atmo, but part within the Atmo website. We also developed Daytimes, which is time series processing toolbox, because when temporal data is typically noisy for all kinds of reasons, clouds and whatever, and eventually you aim to have smooth vegetation products so that it changes only according to the vegetation and not according to clouds or whatever kind of noise. So this toolbox provides you all kind of smoothing and gap filling in case of cloud snow data. It fills up for you the data so that you have the vegetation profiles over time as you would expect. And based on that, you can then calculate start of season, end of season, mid-season, and these kind of phenology applications. And then finally, the classification toolbox works the same as our machine learning for regression. We have over 20 machine learning classifiers. We have a tool that you can select your data that you label. It selects, then it extracts the spectra. You put that into the classification toolbox, and you have all kinds of options, such as accuracy matrix and per class accuracy statistics, even uncertainties for classifying images. Yes, and then maybe the very final slides are that we move towards. So this is again a hybrid method. We combine with Canopy. We train a machine learning model here even with atmosphere. We optimize that, but the key is that once you have these models developed, nowadays we even are able to plug that into Google Earth Engine so that as a user you can run it immediately for any place, any time in the world. You can then do time series analysis. So any variable that you develop yourself, water content, here we evaluated about 10 different variables. We can run that in Google Earth Engines. This is for Sentinel-2 data, so 20-meter resolution. And here are some zoom ins. So we were processing whole Germany in Europe, plus the uncertainties also, I forgot to say. So you can use uncertainty as a mask for all these variables. That's for Sentinel-2. But we also did the same for coarser satellites such as Sentinel-3 that you can process the whole world. For people interested, we provide the codes on YouTube also. So you can see that here. Once you are familiar with Atmo and interested into cloud computing, you can make use of these codes to how to implement these models into Google Earth Engine. And I'm not sure how is the time, if I'm out of time or not, but with this is my final slide. So this is just the conclusions of that what we covered in this talk and what is available within the Atmo toolbox. So with this, I think we can close. And Rabbi, I don't know if there's time for questions or so. It's up to you. If there is time, I saw there are some questions in the chat. Shall we go through it?
Predictive accuracy. It's okay. With respect to biophysical parameter, for example, leaf area index, Li, nitrogen content, and water, equivalent water thickness. So how do you rank them 1, 2, 3 with respect to good accuracy or predictability? Could you hear me?
Yes, but can you repeat the question itself?
Yeah, my question is, with respect to accuracy, which is good, with respect to parameters, for example, leaf area index,
yes,
chlorophyll, and equivalent water thickness, which is more predictable with a better accuracy?
Yes, that's true.
And why so?
Yes, very good question, and I think now I got it. So it's true that some variables we can estimate with a higher accuracy than other variables, and especially leaf area index and chlorophyll content. Those are the ones classically the easiest to estimate. And the reason for it is that these are what we call these state variables. So they have direct influence on the reflectance, and especially chlorophyll content and LAI, they have influence over a large spectral region. So especially LAI as a structural variable, they determine the spectral shape over the whole spectral region, from the visible, but especially in the near infrared in the sphere. So they cause most of the spectral variability, meaning when you have a lot of spectral variability, it's easier to derive a statistical or a physical model from it. Say for chlorophyll content is the largest driving variable in the visible part. So it determines the shape of the visible reflectance, again, because of being the most important driving variable determining the shape. It's the easiest to derive accurate models from it.
What about water?
Yes, water content becomes already a little bit more difficult, because for water content, you need to search for these specific water absorption regions. And these are already more narrow regions, typically within the sphere. Within these regions, they have a lot of influence, but over the whole, they are smaller. So then you need to be more specific, searching for this, those regions, those spectral bands, and in there you can come up with powerful retrieval methods. It just take into account you need to search for these regions or select for these regions. Meanwhile, for leaf area index, you can immediately take all the spectral data.
Okay. Thank you so much.
Thanks a lot.
Again, I would like to thank you. Yeah, we have some question again.
Okay.
Yeah. And come down. Come here.
ARTM to Google Earth Engine. The scripts is available in public domain.
Yes, I think later I will share my presentation with Dr. Rabbi, and he can share with all of you. In one of the slides, we provided the link to the HIT, where you can download those codes for trying yourself. Yes.
I assume that the simulations from the ProCell Pro is made outside, and then it imported in the Google Earth Engine. Then the GPR is trained over that simulated data, which is used for the prediction of biophysical variable. Is it so?
Yes. So you need to first become familiar with the ARTMO software, because there you run your simulations, you train your models. So far, it only works for Gaussian processes. Within ARTMO, you need to export your model, and then once you have it exported, with that additional codes, you can run it into Google Earth Engine.
Okay. Thank you so much.
Yes, thanks.
So, Joe, thank you so much. I know how busy you are writing 2 proposals at the same time, and also your Flex mission review. Still, you could take out your time and had excellent presentations.
Thanks a lot.
So, thank you so much. See you soon.
Okay, thank you. And thank you all.
Right.
Bye-bye.
Bye-bye. So, friends, we have next speaker already has joined online, but we can break for 5 to 10 minutes. Maybe what's time now? It's 4:03. By 4:15, we should join. If you want to go for a break, have a tea and come back. So maybe we can take 5 minutes. Maybe 4:10 you should join, because already he has been waiting since 3:30. So have a quick break and come back. Take your tea down inside and come back. Okay.
দেরি করছে এগুলো ওদিকে নিয়ে যাও
Then average NG mission and science in India. So it is all about, again, average NG mission was an airborne campaign done by NASA, ISRO collaborations. And many of us were part of that program. And it is going to be talked by Dr. Bimal Bhattacharya, who was national coordinator for average NG campaign, science campaign in India. So that was a very ambitious campaign, which was done a number of times. I was talking to you, and that was done by Airborne. That is a manned aerial vehicle. This is a UAV you are talking on manned aerial vehicle, but there was a manned aerial vehicle. So he's going to talk all those details about that. So before that, I think Dr. Bhattacharya is already joined. He has been waiting since 3:30. So thank you so much for waiting, and sorry for that because previous speaker was from University of Valencia, and very interesting topic he was talking of. So let me take this opportunity to introduce Dr. Bhattacharya before he start his talk. Dr. Bhattacharya is associated with the Space Application Center, one of the ISRO organizations at Ahmedabad, since 2000. And now he's a scientist, SG. And he's a alumni of IRI, did both master's and PhD from Agriculture Physics, IRI. And sometimes in 95 with the PhD, and 91 was the master's in Agriculture Physics. Then before he joined ISRO in 2000, he served ICR as a ARS scientist almost 5 years. Then after once he joined ISRO in 2000, he is in different positions in the Space Application Center and involved in many programs of the Space Application Center. I think you know, Space Application Center is more related to the research they do. What are the different applications they can look for, and how those kind of sensors can be developed. So he is from the day one, he has been involved in different strategic and also operational research related activities, and recommending different sensors to be taken up. So he is involved in developing satellite-based agromet services and products and utilizations by National Agromet Advisory Services in India. So he developed different products from the satellite-derived products, which can be used as input for the value-added agro-advisory services. Then he also led the development of satellite-based surface energy balance modeling over Indian terrestrial ecosystem, essentially insert images of Indian geostationary sensors. He led also ISRO GPP program, Global Biosphere Program, national scale science project on energy and mass exchange in vegetation system. He's also the PI of the land surface processes in ISRO CNS Megatropic mission, and science member of Ministry of Environmental Earth Sciences, NERC Indo-UK Monsoon project called Encompass. He is the science leader of average NG, as I told you, of Airborne Hyperspectral mission in India, and also the science co-chair of ISRO CNS Indo-France Thermal Infrared mission, that's called Trishna, which is going to come up very soon on the thermal sensor. He's currently ISRO representative in COs for the land surface imaging. He's the recipient of PR Pisarote Award from Indian Society of Remote Sensing, Young Scientist Award from Asia Flux, Japan, sponsored by the Japanese Space Agency called JAXA. He's also received an ISRO Team Member Award. He's a teaching faculty in UN-sponsored course on satellite meteorology and global climate under Center for Space Science, Technology and Education for Asia Pacific, that is called CSTP, which is at IRS Dehradun, and also Space Application Center, Ahmedabad. He has published more than 50 research papers in peer-reviewed international as well as national journals, and we have been associated since long with the different campaign what we has been done with IRA and also Space Application Center. So warm welcome to Dr. Bhattacharya, and thank you very much agreeing. I know he's not in the office, he's somewhere in another meeting, but he scooped out his time and going to deliver the talk here. So Mr. Rahul is going to move your slides, the slide which you shared, and you can speak from there, and you can indicate to go for the next slide. So thank you again, Dr. Bhattacharya.
Hello. Am I audible?
You are audible bit.
Hello. I think some noises are coming. Yeah. Hello. I am now audible clearly.
Yes, sir. You are audible here.
Okay. So I think I can start now. So first of all, thanks to Dr. Ravi. Thanks to Dr. Ravi for inviting me to give a lecture. Hello. 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 Am I audible? Hello. Am I audible? I think some echo is coming. Okay. So now my best compliments to Dr. Ravi for organizing such a good workshop for digital farming, which is very relevant in India for the next part of the green revolution, where actually crop yield actually has stood at a plateau region. So we have to increase the yield as well as we have to give the less input. So the resource input efficiency has to be increased. For all these things, the different digital technologies are very, very important to use in agriculture. So the outline of this, my talk is on basics of imaging spectroscopy and hyperspectral science, and then data structures, visualization, and what are the different global initiatives. And then I'll brief on the different flights of Everest NG Airborne hyperspectral science campaigns over India, and also the examples from Airborne as well as some spaceborne reflectance spectroscopy, science and applications for agriculture, their future scope, open data, and future missions. Can you go to next, please? Rahul, can you go to next, please? Yeah. So imaging spectroscopy, I hope that you have already been taught, but still I need to give some basics that when photons interact with the molecular structure of surface materials, it gives you the characteristic or diagnostic absorption features or overtones, either in the reflectance domain, that means in the 400 to 2500 nanometer, or in the emitter spectra, that is in the thermal infrared region. However, these absorption features actually take place due to energy transition, which may be through the electronic transitions from atoms in a molecules or lattices. These electronic transitions actually occur at very shorter wavelength, and vibrational transitions which occur at longer wavelengths. And these particular two type of energy transitions actually form the basis of whole of this imaging spectroscopy either in the reflectance or the emittance domain. And these vibrational transitions will be having the different bending stretches, and because of these you can get the dominant spectra as well as the overtones which occur at the sums or multiples of the fundamental vibrational frequencies. Next one, please. Yes. So what do you mean by hyper? Hyper means that you should get the huge number of narrow contiguous bands, and it should not be the discrete bands as exemplified here. That suppose from 400 to 2500 nanometer, if you get the bands, so here if you get the discrete bands like different multispectral sensor, so you may not be able to distinguish different targets or different materials, or here the case is for minerals. However, if you get the continuous spectra, so that you can capture better the different absorptions like greater than 2000 nanometer, and as well as somewhere in the shortwave spectrum, in that way you can distinguish different type of the minerals. So similar way, if we go to the vegetation, next one please. Yeah, if you can go to see the vegetation, here also you can very well distinguish from one species to another species based on the whole spectrum of the vegetation. However, in the VNIR spectrum, which is spreading between 400 to 1000 nanometer, there you will primarily see the absorption due to the chlorophyll, or the reflectances which are varying due to the leaf structure, which is called, which is actually reflecting on the NIR portion. And when it is more than 1000 nanometer, those there actually primarily water as well as the different organic compounds play a very important role to discriminate between the spectra. So, however, if you take the multispectral, here also you can get the discrete bands, though you will get some differences, but you will not able to actually get the absorption due to the different constituents of the canopy. So that actually limit your analysis or the quantification. So for better precision of the quantification of the different constituents of the canopy, the hyperspectral is very, very needed, and it is desired than the multispectral. Next one. So similarly, it is the case of soil also. So if you see that in case of soil on the left hand side, that here for the different type of ions in the soil, here mainly the when charge transfer and crystal field theory are dominating, which actually relate to the electronic transition of the energy. There also actually most of the absorption actually take place below 1000 nanometer. However, in the longer wavelength, which is more than 1000, their vibrational charge transfer, actually energy transfer, actually occurs dominantly. On the right hand side, if you see that when if you plot the spectra of the simple soil, where this organic matter actually plays very important role between 750 to 1150 nanometer, and iron oxides around 550 to 750, and also hygroscopic water and different clays and organic matter on the higher wavelengths. So a very good examples are given below, where if you see that if you have the organic matter, so here you can get the different sort of the spectra, and where the iron oxides is removed from soil, so you will miss some absorption due to iron oxides. So the reflectance pattern will be totally changed. So depending on the removal and the addition of the different constituents like organic matter, amorphous material, iron oxides, so you will get the different concavity of the shape in the spectra, and that determines the discrimination or detection of the presence and their abundance of the different constituents of the soil. So next one, please. Yes. So if you see that levels of information, if we go from panchromatic image to multispectral to hyperspectral, basically with the panchromatic single band, which go with the only detection, and then it moves to classification, discrimination, identification for multispectral. But when you get the hyperspectral, they are actually, we are quantifying the abundance of the material. So that is the power of the hyperspectral data. Next one. So this is showing the 3D data cube, which is the conceptual visualization. Here, if you see that, if you start from the if you see that if you get 400 spectra for a given pixel, so your pixel is a raster image of X and Y. So your Z direction, there will be spectral bands. So if you stack those spectral bands, you will get the 3-dimensional image in the form of 3D data cube. So in that 3D data cube, if you see the vegetation pixel, so it will have unique spectral curve, and where you can see that contrast between red to NIR and several absorptions in the shortwave infrared and the various points of near infrared also. But if you go to water, it will give you the typical spectra only up to the 1000 nanometer, but after that reflectance actually decreases a lot. And then similarly, if you go to the atmospheric part, if you will see a lot of absorption happens due to the atmospheric constituents. So hyperspectral actually is very, very important for all these three: atmosphere, land and water, this constituents estimation and their abundance estimation. Next one. Yes. Now, here I would like to show that this is the airborne hyperspectral image, and this is the typical false color composite. And this on the left hand side, there is the L1 data that is called the top of atmospheric radiance data. That is the level 1 data. That means from the aircraft, you get the raw data, which is called the level 0. And that raw data is calibrated and also reprocessed because of some anomalies you get. So after reprocessing, you get this level 1 data, which is the geo-rectified and the calibrated radiance data, but not atmospherically corrected. So what you get is the radiances in the different spectral bands of top of the atmosphere, that is called the TOA radiance. When you go for the atmospheric correction, then you get the surface reflectance, and that is called the level 2 data. So this is one actually data cube which is being shown for agricultural region over Muddur in Karnataka, which is actually acquired from every Senji fly. Next one. So if you see that 3D data cube, you can see in a vertical way also, and you can see at the horizontal way also. So this is the way different type of the data cube is you can visualize. But when you can display the 2D, suppose for with the natural color composites, where blue band will be there. So the below images actually are showing the 2D images, basically the natural color composites, or you can display it in the false color composites. Next one, please. Now, there are a different type of airborne platforms and sensors available. Primarily for airborne, we use aircraft and the UAV or drones and so different type of the sensors or instruments are available for airborne hyperspectral campaign. Hyperspecs is one of them, is very useful, and also the Everis, which has been developed by JPL NASA. So these are two actually very, very high level of instrument, which gives the good fidelity of the hyperspectral data. Next one. Now, there are other airborne spectrometers which are available, like HIMAP from Australia, then CASI, then DAIS, then ROSIS, then EISA, HIDICE, and MIVIS. So nowadays several different private entrepreneurs, they also have developed different airborne modules of the hyperspectral data, and it can be easily flown on drone, very lighter weight. Hyperspectral sensor are also available, which are being flown on the different drones, and you can get very good data for actually the centimeter level of data, which can differentiate from one plot to another plot and their spectra. But one thing you should keep in mind, that the more the finer resolution will be, more the complexities in the data analysis will be and the interpretation. Next. So ISRO has already earlier developed some hyperspectral payload on spaceborne platform, which are called the AIMS, and then High-C, and also the advanced High-C. Now these here, the spatial resolution actually vary from 30 meter to 3.5 meter. However, the spectral range were only limited to 420 to 950 nanometer. And the number of bands are okay, means 512, and different number of bands were there. But main thing is that the signal to noise ratio were very, very low. Similarly, NASA also has launched earlier EO1 Hyperion on the spaceborne platform, though it was having 2 to 4 bands and 400 to 2500 nanometer range. However, at 30 meter resolution, however, here also the SNR was very, very low. So next one, please. Now, this paper of Transon 2018, it gave a good review of that what are the upcoming sensors in the spaceborne platform. So in the hyperspectral from the hyperspectral mission. So if you see that after Hyperion, there are Tiangong, Prisma, High-C, and then in future there will be KIME, then there will be SBG, and there are a host of NMAP. Already the Prisma and NMAP have been launched, and if you see the peculiarity or uniqueness of these all these spaceborne sensors, you can see that their SNRs are very, very critical, and they are actually higher, substantially higher than what has been done in the Hyperion, EO1 Hyperion. So the more the SNR, the more will be your discriminability or the quantification ability using the hyperspectral data. Next one, please. So these are the other sensors like NMAP, which has already been launched by German Space Agency. And then there will be a commercial satellite of hyperspectral that is called Shalom between Israel and Italy collaboration. Then there will be Hesperi mission, that Hesperi is named as the SBG, that is the surface biology and geology, that will have both optical bands in the hyperspectral region as well as also thermal infrared band. And there will be Hispex also. So if you see all these cases, there are substantial improvement in the SNR and also the spatial resolution varying from 10 to 30 meter. So revisit period almost everywhere it is restricting between 8 to 16 days, so that we cannot compromise too much. So so we expect that from Prisma, NMAP, and the host of hyperspectral sensors in the future, there will be a boom in the hyperspectral application, both from spaceborne missions as well as the drone-based hyperspectral data. Next one. So ISRO and NASA collaborated on Everest NG Airborne Hyperspectral Science Campaign over India. And you can see on the left-hand side, the Everest NG instrument. And in the middle, there is B-200 aircraft, which has been given by ISRO. So ISRO's aircraft was used, and where Everest NG instrument was integrated, and then a flight took place in the several sites of India. And you can see that there are a lot of academia from both US and Indian sides who are involved, where Dr. Rabi from Indian Agriculture Research Institute and from DST also several scientists were took pioneering role in the involvement of the Everest NG flight campaigns and actively analyzed the data later on. So this campaign took place during 2015-16 and 2017-18 periods, and we had the host of workshops spread over 2017 and 18. Next one. Yes. So there were two phases of Everest NG campaign. Phase 1 campaign actually took place during December to March 2015-16, and it carried over for 84 days, and it actually covered 22,840 square kilometer over 57 sites from 10 air bases of India. And phase 2, if you see that there were two parts, phase 2A and phase 2B. So phase 2B could not take place. Today we have one meeting with US where we will be deciding that whether we should go for phase 2B or not in the coming years. But phase 2A campaign, it covered actually 48 sites. So the flights took place during February to May of 2018, and it was carried over more than 15,000 square kilometer for 80 days from 6 air bases of India. And mainly these sites, which totally actually covered the 105 sites, and these sites actually cater to the different scientific themes like agriculture ecosystems, then mineral resource mapping and geochemistry, coastal and ocean, rivers and water quality, urban and cities, snow and ice hydrology, atmosphere and calvert. So these are some of the examples over agriculture, then coral reef and coastal, and then geological sites. You can see the 3D data cube from Everest NG. Next one. And these data actually site-wise, these are kept in our geoportal that is called Vedas geoportal, vedas.sac.gov.in. You can note it down. If somebody is interested, he can actually get a login from Vedas of SAC through your institutional ID, and then you can download these Everest NG hyperspectral airborne data for your site of interest, and then you can further analyze those data, and you can play the data with the satellite data, or you can do different sort of analysis. Next one. First of all, when you get the L1 data, so you need to calibrate with the ground level of information. So that calibration validation site should be very uniform. So we had one calibration validation site that is called Desalpar, which is mostly in the desert and uniform site, and there the corresponding to the Everest NG passes, the atmospheric measurements on aerosol, then water vapor were noted, and then also spectroradiometer data were also collected. Then those were actually correlated with the Everest NG tour radiance, and whatever gain and offsets we have got, those have been fed into the L1 data, and then those data have been made the calibrated data. So this is one kind of flowchart which is actually gone into the calibration of the airborne data. Whatever airborne data you get or drone-based data, you need to calibrate those data for some of the atmospheric conditions. Otherwise, you cannot get the good discriminability across the sites. Next one. So once you get the L1 data to correct the tour radiance, so next part is how to eliminate the atmospheric interferences, especially the water vapor, CO2, and also the aerosol optical depth. So you have to do the atmospheric correction for different pixels. So in ISRO, in Space Application Center, we have developed in-house algorithm for the line-by-line correction of line-by-line atmospheric correction model, which actually from TOA radiance itself retrieve the atmospheric parameters like aerosol, water vapor, and the CO2, and those are fed into the model, and then those other radiances which are mostly governed by the reflectances, those are actually corrected, and you get the surface reflectance product. So these in-house algorithm we have compared with the NASA algorithm, and then we found that our algorithms in some mostly it is matching with their algorithm as well as with the ground-based spectra. Next one. So on the left-hand side, if you see that it is the uncorrected, atmospherically uncorrected product, and you can see a lot of haze in the scene. But after atmospheric correction, you can see that most of the hedges have been removed. So this shows the power of the atmospheric correction between L1 to L2 product. But definitely, if hedge conditions are very, very high, so you cannot completely remove all the hedges, but you can reduce their intensity or their interference into the overall surface reflectance. And this shows on the right-hand side, shows that how the radiance spectra vary over different sites, and when you are converting into the surface reflectance, how they are looking like. Next one. So for hyperspectral data analysis, there are different techniques, and these techniques depend on how you would be, what is your interest of study. So some people are interested in the dimensionality reduction, that they would like to figure out the minimum number of bands which are required to further investigate their scientific interest. But some people are interested about the typical absorption position and their band shape parameters, absorption band shape parameters, so that they can use it for different type of analysis, and where continuum removal method is actually largely followed. And you can see this continuum removal technique, which is largely followed, and where you will get that exact absorption in a magnified manner, where these band maxima, then FWHM, all these different sort of even band area, all these parameters you can derive, and you can use it for your analysis. Many people are using these different bands for classification, and these since it is a huge, enormous amount of data, like 420, every CNG has provided 425 bands over 400 to 2500 nanometer, and that is spreading, that is at the spectral interval of around 5 nanometer. So different machine learning algorithms you can also implement. It gives you the large scope to use the machine learning algorithms for both classification and also the classification and also prediction of the different quantities of the canopy and the soil constituents. And these evidency data are very good data sets for using any sort of canopy radiative transfer modeling and their inversion. So suppose ProSail, DART model. So I think you have heard already the very in-depth lecture on the canopy radiative transfer modeling using ProSail by Joachim. So, so there is enormous scope with this sort of data, and this evidency data is giving you the resolution, spatial resolution of 4 meter to 8 meter, and it has the SNR of 1:2000 at VNIR region, and the SWIR band it is 1:1000. So with this kind of SNR and with this kind of resolution and this much enormous amount of data sets, you can play with the data in various means for your interest. Next one. So I'll just show you some of the examples. I'll first give you some example typically on the crops. We are actually dealing with the crop classification, especially to determine the mixing of the crop in a given region, how to unmix that. So next one, please. So, yes, so this is the typical example at Kota region of Rajasthan, and you can see that how these different spectra of the crops are clearly distinguishable. Even the minute crops are also clearly distinguishable from these different spectra. And mostly for the crop type discriminations, these actually fall in the VNIR region. But if you would like to quantify different canopy parameters, you have to take both SWIR band as well as the VNIR band for the quantification. And when we have checked when we have compared the accuracy of the single date Aviris NG data and the single date multispectral data from the space-bound platform of equivalent, almost equal spatial resolution of 5 meter from LIS4 data, we have seen that Aviris NG has given 77% accuracy, whereas from LIS4 single date, we can get only 47.3% accuracy. So you can see that if we get some 3-4 dates from hyperspectral data, it has the power to eliminate the constellations of large amount of multispectral data. So you just think that how judiciously you can use, though there may be some compromise between the hyperspectral and the multispectral, because hyperspectral spatial resolution from the space-bound platform you cannot achieve beyond 20 meters as of now. So you can think of using both hyperspectral and the multispectral together to generate or to have the classification at the 5 meter level, but taking the resolving power, spectral resolving power of the hyperspectral data. So next one, please. So this is typical example from Dr. Sahu's work, who has carried out tremendous campaign in Bhagalpur region, which is a horticultural orchard. And you can see that how these spectra are getting differentiated for the different type of fruit crops. And you can get the different fields of the fruit crop distinguished I think there were some 10 to 12 fruit crops, which if you see on the natural color composites, you cannot distinguish, only tone from dark to light you can see, but from the spectra, yes, you can very well distinguish and classify the region. Next one, please. Yes. So this is typically one example of distinction between mango and sapota, where actually over Gujarat Talala region, when we were carrying out some project in the Chaman from the ministry side. So we found that in some of the pockets, you cannot distinguish, spectrally distinguish using multispectral data between mango and sapota, because its morphology, texture, all these things coming almost similar in the multispectral data. But when you are using the hyperspectral data and also genetic algorithm in that, so you are able to distinguish the mango and sapota. So hyperspectral data has, especially airborne or that 5 meter kind of hyperspectral data has that kind of power to distinguish, to have the minute distinctions between the two apparently similar type of morphologically similar type of fruit crops. Next one. Yes. So actually in crop classification, I have already told that you have the choice and you have the freedom also to have lot of spectral bands and continuous spectral bands. So it drives the opportunity to go for the crop classification using the AI and ML modeling, where this deep neural network modeling framework has been established. And over another region, we could see that from the conventional classification, this deep neural network model actually has given the lot of variability in the crops, and also it gave the better accuracy as compared to the conventional classification scheme. Next one. So in the crop, after crop classification, next is the how we can quantify the biophysical and the biochemical parameter of the canopy. So I'll give some of the examples. Next one. Yes. So finally, when you are going for that, you need to have canopy radiative transfer modeling. This canopy radiative transfer, you know that ProCell is our basic model, and it actually simulates, when you have the forward simulation, it simulates the spectra in different spectral band continuously from 400 to 2500 nanometer. And first we could see the sensitivity of the different constituents of the canopy, and you can see the chlorophyll content. You can get better sensitivity up to the 700, less than 700 nanometer. And after that, in the near infrared region, around 800 to 1000 region, you will get the more sensitivity for the varying leaf area index, because it relates to the structural part of the spectra. But on the shortwave infrared part, you can see that it is more sensitive to the leaf water, changing leaf water content, whether the other bands are not sensitive to the leaf water content. So this gives you the large flexibilities that how you can retrieve chlorophyll content, then LAI and the leaf water content. And these can be along with the other parameters like nitrogen and many and finally have the abiotic stress, how much abiotic stress crop is having. So to know that. Next one, please. So this is typically showing which we have done in Space Application Center using ProCell model, that you can do the simultaneous retrieval from the hyperspectral data, simultaneous retrieval of the chlorophyll, LAI, and leaf water content. But if you go for multispectral data, you cannot have the simultaneous. You need to have some approximation to take to So first, actually, you have to generate the synthetic database through lakhs of forward simulation. And from the synthetic database, you can get the inversion once you get the surface reflectors from the airborne data or the spaceborne hyperspectral data. So while inversion, you can get hello, hello, hello. Next one, hello. Hello, hello. Am I audible? Next one, please. Hello.
Yes, sir, you are audible, sir. You can go ahead.
But I am not able to see that slides are moving.
Now it is moving, sir.
Okay, but my end it is not. Yes, it has come now. Okay, so if you see. From the multispectral data, those we have compared, and we found that this hyperspectral based retrieval actually had given you the far better accuracy than the AWIPS data. On the red dots, you can see the retrieved LAI from multispectral, and in the blue colored dots, you can see the hyperspectral based LAI retrieval. And these are the different maps of the chlorophyll content and deep water content and the LAI for a given region. And this is the simultaneous retrieval. Next one. Yes. So apart from these, you can go for the derivative analysis, first derivative, second derivative analysis. So typically nitrogen content, when it is varying, it will show up absorption in the red edge region. So there is a green peak as well as the red peak, and this red edge actually shifts from left to right depending on the variation of the canopy nitrogen. And this peak of the first derivative actually were correlated with the measured canopy nitrogen content, and we have fitted the model. We found that it has a very good correlation between these two, and those were mapped. And when we have got the nitrogen, we have got LAI, we have got water and chlorophyll. So we can use judiciously with some weighting factors, we can come up to the abiotic stress mapping of the crop. Next one, please. So now, when we have retrieved the total chlorophyll, we have made an attempt to distinguish between chlorophyll A and chlorophyll B. And you can see that structurally, this chlorophyll A is little different, that it has the methyl component, but here it is the CHO component in the chlorophyll B. And due to these reasons, you can get little different absorption peaks between these due to this chlorophyll A and chlorophyll B. So Average NG 5 nanometers spectra, though it is not sufficient to distinguish between these two absorption peaks, but still advances in space research by our team, and we call it a non-destructive estimation of chlorophyll A and B using the imaging spectroscopy observations. Next one, please. Next one, please. We are going to preview. Hello. Yes. So you can see the validation. Validation is not so good for chlorophyll A and B. However, you can see that spatial distribution of these two parameters from the average NG data. Next one, please. Yeah. Hello.
Yes, sir, we are getting, sir. Continue, sir.
Yes. Next one, please. You go to next one. Yeah. Yes. When you get the different sort of parameters, then using the different combinations of chlorophyll, water, LAI, and canopy nitrogen, you can have the canopy abiotic stress of the crop. And then you can level it into different stress levels of the high stress, moderate stress, and the normal health. So within a farm, you can see that how these stress levels are different across the different field conditions. So these can be possible once you retrieve the quantity of the biophysical and chemical parameters rightly from the hyperspectral data. Next one. Yeah, so another example is that how we can detect the disease from the hyperspectral data. So here over Punjab region, we had the Ropar region where we found that there was infestation of the wheat yellow rust, and we could collect we had the Everest flight that time, and we could collect the ground spectra also. And based on that, we could find out what is the sensitive bands of the healthy and the wheat rust based disease spectra. We found that actually between 550 to 600 nanometer, there are some sensitivity, but most sensitivity actually occurs beyond 2000 nanometer. So, and on the left hand side, you can see the details and the zoomed portion, how these two conditions are different, actually putting impact on the reflectance spectra. So using these two, you can very well distinguish the diseased and the healthy plots from the Everest hyperspectral data. Next one. So in the crops, we could actually detect the crop residue based on the some specific bands. Go to next. Yes, so you can see that just over Sundarban area, when Everest flight took place during March period, that time this Canning region where was actually full of the crop residue after the rice was harvested, and that residue actually here, if you can see that some of the bare fallow plots in the spectra, their spectra beyond the 1300 nanometer and also below that, you can get the higher spectra in the red and violet color region beyond 1300 nanometer region. You can see that well segregated from the blue color spectra, especially in the 1900 to 2300 nanometer. So that gives you that, because the residue actually is lying over the bare soil. So from the bare soil spectra, you can expect, because of the cellulose and the lignin content of the crop residue, you can expect better reflectance, especially in the 1900 to 2300 nanometer. For using that criteria, we could actually distinguish we could actually estimate the rice crop residue cover fraction using the hyperspectral data. And when you have generated the crop residue, to know that how much nitrogen content it is adding to the soil, so we use the normalized difference nitrogen index using the 1510 nanometer and 16180 nanometer. This 1510 nanometer is very, very sensitive to nitrogen, and 1680 had been taken to remove the water part, water effect from that. So using these two, we could actually estimate the residue, nitrogen of the crop residue, and finally it can lead to the how much CN ratio it can modify in the soil. If you turn it into the soil, how much it can add into the soil. Next one. Now in the soil, prediction of soil physicochemical properties are another application area where hyperspectral data can very well be useful. Next one, please. So soil types in the bare soil, you can very well distinguish. This is Ikrisat region of India, where you can see different type of soils association together in a very large region. So every Everest flight was carried out, and this has been useful to characterize and see that classification of the different types of the soil with a good accuracy. Next one. So soil carbon. So there are different forms of soil carbon, like soluble organic carbon, then inert organic carbon, humus carbon. So from Punjab State Remote Sensing Center, they were also part of our Every team, science team. So they could come up with a partial least square regression model using the large amount of soil samples they have collected from the different Every sites, and they have the ground-based spectra, and from that they could identify some of the important wavelengths in the very shorter wavelength, near infrared, and the shortwave infrared region, and they could come up with a very good PLSR model for estimate the soluble organic carbon. And you can see next one, please. Soil organic carbon map over Anand region, though Anand region is having very less amount of soil organic carbon, but still you can see that some of the pockets which is having still a little higher organic carbon, soil organic carbon, as compared to the other region, and those minute regions also have been picked up using the Every data. And recently, some work has been done with similar data sets to find out the presence of the heavy metal in the soil of this region. Next one. So another very important problematic area is to how to have the good quantification of the soil salinity, especially into the low to moderate soil salinity where crops are actually grown. So during the dry season, from the 6 sites from India, soils have been collected, and those electrical conductivity and many other parameters, soil moisture, have been measured, and every flights were there, and then absorption bands were identified, and different ensemble machine learning algorithm has been established to predict the electrical conductivity, and then based on that, a new hyperspectral soil salinity index has been defined, and this paper is revised for ISPRS photogravity and remote sensing. And this is a very good, robust kind of soil salinity index. Using hyperspectral data, we could show its superiority as compared to conventional multispectral and other regression-based soil salinity measures. Next one. Yeah, next one, please. We could do some of the earlier work using the hyperspectral data, especially the spaceborne data with U1 Hyperion. This is one case study with U1 hyperspectral data over Bharatpur region in case of master rot disease. Go to next, please. Where you can see that before infestation, you cannot see the as per the different disease intensity level, you cannot distinguish the VNIR region very clearly, and also shortwave region, infrared region especially. But after infestation in the shortwave infrared region, it is well distinguished. And based on the different bands, we could do the canonical correlation and discriminatory analysis. So band selection method and also index selection, two-step discrimination analysis were carried out, and we could find out a unique index to the rod, and which actually was mapped to know the disease and the healthy crops from the hyperspectral spaceborne data. So this paper has been published in the Computers and Electronics in Agriculture in 2013. Next one. So our knowledge of the nitrogen estimation and the fast derivative analysis, we could extrapolate our knowledge of Every's data were very useful to estimate the canopy nitrogen using the hyperspectral data, though we got the lower estimates of the range of the nitrogen as compared to what we have got from Avery's hyperspectral data. So again, I reiterate that spatial resolution as well as the signal to noise ratio, it actually has a lot of things to rightly quantify and get the right range and the variability of the type of the parameters you are going to determine using the hyperspectral data. Next one. So ISRO is planning missions of GISAT, and it will have the multispectral as well as hyperspectral and the long wave infrared. But hyperspectral data, it is the experimental payloads. It will be having relatively coarser resolution of less than 300 meter. However, I think the researcher will get the scope to use these data because this will be a weekly data and use it with other good hyperspectral mission of finer resolution to have the meaningful results. Next one. Yes, so ISRO has come up with an advanced hyperspectral data analysis software, and this beta version of the software you can download from Veda's website, and our knowledge and expertise has gone into this development of the software, and researchers and students can download from Veda's site and use this software, and they can give the feedback to us. Next one. Yes, then presently you can have the Prisma data from Spaceborne platform, which is having 30 meter spatial resolution. I had the opportunity to present our every century results in the Prisma workshop last year. And NMAP has been launched by German aerospace agency, but those data have not been released yet. And apart from that, there is DESIS, which was the precursor to NMAP mission, but DESIS has the restriction in the wavelength bands of 400 to 1000 meter, 1000 nanometer. So you have the host of possibilities of 20 to 30 meter spatial resolution hyperspectral, as well as future GISAT from Indian Spaceborne mission, which will be having less than 300 meter. So you will have a lot of scope to play with the data to go for the advanced modeling, retrieval, and find out the new scientific results and techniques, so that it can be helpful for fulfilling the aim of the digital farming over India. Next one, please. Yeah, and NASA is also planning a very high-end mission called the Surface Biology and Geology, which will be having not only VNI and SWIR hyperspectral, it will be having also MWIR and TIR also channels, hyperspectral channels. So, but these will be launched during 2029-30 period. So, what I mean that for the researchers, there is a tremendous scope of in the future lying ahead using both drone and the spaceborne data, and to use simultaneously for the digital farming of India. Next one. Yeah, we have several publications as a scientific report from every SNG. Then current science, we have the full special issue. Then we have the Spectrum of India, some book in the Elsevier, where I have also one of the editors. It is available, and now another special issue in advances in space research is coming up, which is in the process of the publication. Maybe within the next 6 months, the whole volume of this special issue will come up. So with that thing, I end my talk here. So if you have any questions, you can put it before me. Thank you. Thank you very much. Hello.
Yeah. Any question? Audience? Students? Rajkumar, anything? So,
Hello.
sir, I think we don't have any.
Yes.
Yes, I have a question. I have not
And,
actual question.
online, any chat box, any question is there?
Yes, sir. Excuse me. Can
So-
I speak? Can you hear me?
No question also is there online. Around 95 participants are there.
I am able to
And,
hear someone wants to
Thank you so
question.
much for such a
Hello.
lucid and
Can I ask one
excellent,
question?
talk about the joining of ISRO with respect to hyperspectral sensors and also future plans. I think we have taken backseat of hyperspectral sensor from ISRO. I hope soon it will be launched. Maybe your initiative is required, and then we can really start working on that. So we are now limited to airborne only, but hyperspectral we don't have any sensor, and we are dependent on Prisma and all those foreign satellites. So thank you very much, sir, for taking out your time. I know you are scheduled somewhere else, and you did your presentation from mobile, and but it was really excellent. And thank you again.
Okay, thank you.
So wind up. So online participants, I think we'll resume tomorrow. There is no class, and Monday at 9:30 we'll start as early as possible, because we have totally packed sessions, and we have speakers from Europe and also from India. So that is going to be these 2 days is going to be very hectic for us. So we'll have lab and also field practical sessions. So we'll start at 9:30. Don't be delayed. So that's what my request. Tomorrow and day after, you are free. You can go around who are from outside Delhi and enjoy bright sunshine and go around, move around Red Fort, India Gate, whatever you like to go for shopping. Otherwise, every day 5:30 you are leaving this place, so you don't have time to go around. So see you on Monday. By 9:30 you should all be here. Okay. Anything? Any question you have? All these materials are going to be available in a compiled form to you, so don't worry for that. Okay. And we have taken also group photograph on the very first day. So that photograph with the certificate we are going to get, and already corrected names are there. We have. So soon we are going to make the certificate ready. Again, we have also evaluation form, and Dr. Rajkumar and Dr. Rajiv, they are going to distribute last day only. Last day means maybe on 24th itself, they will distribute. You have to fill up and give us. So that is what the criteria from the World Bank. We have to get that. So with this, we end today's session, and see you on Monday, 9:30 again.